And in fact, today on my morning walk, I was very lucky to pick up a few flowers. This is a Tsafa and this is Prajakta. And these flowers actually talk to me when I walk past them, and they keep reminding me to always be grateful for two things that we have. One is, of course, Mother Nature blessing India every day. And the second is, friends, wonderful technocrats who work with the ground, they work with the sky, they work with the wind, and they work with the natural forces, and they make our life a better place every single day. So, on this note, ladies and gentlemen, students, all you wonderful people who have finished their breakfast and their walks and are having a cup of coffee like I'm doing here, and who have diligently logged on time for this webinar, a very, very warm welcome from Epicons EFC, and in fact, all the speakers who are going to be sharing their wonderful knowledge and years and decades of experience with each and every one of you live. On this note, I would like to introduce Engineer Jain Kulkarni, who is a friend, who is really somebody that I'm very grateful to for involving me in these webinars. So coming up next, a formal introduction of Jain Kulkarni sir. Please stand by. It's a great pleasure and a moment of great honor for me to be introducing Jain Kulkarni, engineer who represents Epicons Friends of Concrete. A brief introduction about him. Of course, he is a BE Civil from VJTI Mumbai University in 1976. I think the 70s were very interesting times to be an engineer in a developing country like India. He followed this up with ME again from VJTI in 1978. His areas of interest are diverse, from the technical field, if I were to mention, codal provisions, seismic retrofitting, tall buildings, concrete mix design, advanced NDT and evaluation, conservation of heritage structures using technology and sensitivity, Indian aesthetics, construction chemicals, and of course, apart from the professional angle, he is a person who's very fond of so many other things. As the technical administrative head of Epicons Consultants Private Limited, he has huge responsibilities on his shoulders. And these shoulders and this work style has already finished more than 9,000 projects completed, friends. Just imagine the things that he has seen in this field. To give a few examples, as you can see on the screen, Runwal Greens and all these wonderful buildings. I would like also to mention the awards that Jain Kulkarni has received. Just to mention just a couple of them, he has received the Institute of Engineers Award for Industry Excellence in 2021. And not once, this has been the second time that he has received this extremely prestigious award. I think it's a great matter of fascination for me also as to how a technical person can indulge in sharing knowledge not only for him and his team, but for the fraternity at large. I would like to name a couple of more recognitions. In 1999, he was also felicitated for the Modern Knowledge Dissemination by India chapter of ACI. I think that's a recognition of the fact that Jain Kulkarni, along with the fantastic Epicons team, is consistently sharing knowledge, disseminating the years of experience and excellence to the entire fraternity. Now, on this note, this was a very short presentation and introduction of Jain Kulkarni sir. Jain Kulkarni sir, over to you for the formal presentation of EFC. Thank you, sir. Over to you.
Good morning, everyone. I welcome you all to webinar 149, Design of Tall Buildings for Wind and Seismic Forces. Am I audible properly?
Yes, you are.
Good. So next. EFC started organizing workshops from 17 September 1999, and it became platform for exchanging thoughts about latest development in the field of civil engineering, much before Epicons obtained ISO certification. Next. Epicons Consultant Private Limited is ISO 9001-2015 certified company. One of the well-defined objective of Epicons is imparting technical knowledge to the interested parties and society at large. Next. However, we started our workshop series much before obtaining ISO certification. Our principal is inspiration, friend, philosopher, and guru, late engineer A.P. Remedios. Next. So there are two photographs from the physical workshop which were carried out at Sarkot opposite Visitia. EFC has conducted 86 workshops in last 25 years and 48 webinars in last 4 years. EFC started webinar series much since lockdown through our dedicated unit EFC. EFC is a humble effort to create knowledge sharing platform and develop a facility for continued education for practicing structural engineers, corporate consultants, government, semi-government authorities, architects, builder, and of course, faculty and student, because everything happens for student through faculties. Today, we are at webinar 149, Design of Tall Building for Wind and Seismic Forces. And our next physical workshop will be at Visitia, Role of Civil Engineers in Climate Change Mitigation on 19 September 2025. It's a novel way of celebrating Engineers Day on 15 September. Next. With this, I introduce my team. From left side is Arvind Parolekar, architect Parashar Moge, engineer P.P. Pandey, myself, engineer Ravindra Deshpande, engineer Anil Joshi, and engineer Anand Kulkarni. These are all directors of Epicons, unit heads of Epicons, taking Epicons further. And for every workshop, webinar, all of them are involved. Next. With this, I thank you very much. This is a photograph of our entire team. Photograph is old one, but most of the team members are still today. So I hand over to Priya.
Thank you, sir. That again was an extremely short presentation by the Epicons of the Epicons and AGFC. And of course, there's a lot that is very interesting on the Epicons website. And I really request all of you to once again go to their website and see. I find it extremely interesting and fascinating. So, friends, moving on, I now have the huge responsibility of telling you a little about myself. I run a company called Wide Angle Forum, and we are a small company based in Pune, and we do events. We have a design publication called Design Vista. We conduct study tours for anybody working in design, lifestyle, and construction. We love connecting people together, and that's why our tagline is Connecting Creative Minds, because I believe everybody who is born a human being is a creative person, and I would love to connect with all of you. Once again, I want to thank Jen Kulkarni and the Epicons team for making me a tiny part of this extremely important presentation. To move on, I am now assigned to give you a preamble of this workshop, and I'm reading now. Good morning, esteemed guest speakers and participants. Welcome to Epicons Friends of Concrete, webinar number 149. As you already know, EFC aims, that's Epicons Friends of Concrete, aims to bring together experts, professionals in the field of structural engineering to share knowledge, their experiences, and very important best practices. Don't we agree that that is so important nowadays? This is the 149th webinar organized by Epicons EFC. And the title of this, as all of you know, is Design of Tall Buildings for Wind and Seismic Forces. And we are very thrilled to have Dr. Lakshmi Parameswaran and Dr. Yogendra Singh sharing their expertise with us today. Big round of applause at our own end for both of them. You know, if we were sitting in a hall, I'm sure the hall would be full of appreciation, affection, and thanks for these two individuals who have spared so much of time to be here today. Now, I would like to emphasize on what is the need for this, just in 15 seconds. Friends, all of us know, even the layman who's walking on the street knows that there is suddenly a glut for the need of high-rise buildings. Obviously, India is an aspirational country. We want to live well, we want to grow in our personal and professional life, and there is no alternative but for high rise really mushrooming across the country. No doubt right now this may be limited to the metros, but this is all the more reason why research, development, sharing of knowledge, and technological application has to be there while construction high-rise buildings. Moving on to this particular webinar, as all of you know, Dr. Lakshmi Parmeswaran and Dr. Yogendra Singh are renowned experts in structural engineering with extensive experience in designing and analyzing buildings for various loads, including wind and seismic forces. Their tremendous research, their papers, and practical experience will provide valuable insights to all of you, and I'm one of the audience too today. The webinar topic, which is design of tall buildings for wind and seismic forces, is, one can safely say, a critical aspect of structural engineering, more so today. With increased urbanization and infrastructure development happening like nothing ever seen before, it's essential to ensure that buildings are designed to withstand natural disasters like earthquakes, strong winds, and our speakers will cover the key considerations, design methodologies, and practical applications. Of course, we shall also be having question and answers. So definitely this is going to be a lot of interaction during the webinar. I assure you of that. To put in a nutshell, what we'll be covering in this whole day workshop. Number one, understanding wind and seismic loads. Of course, that's the title of the workshop. Design methodologies and codes. It is an essential part of the way processes are made. And of course, case studies and practical applications. I'm personally a huge fan of watching how projects take place. Now, the objectives, while there are many, I would like to make it very precise by citing three objectives. Number one is to enhance understanding of wind and seismic design principles across the segments of engineering, architecture, structural design. Second, learn from the expert experiences and case studies. And third, network with professionals and academics, which is actually happening as I speak. I'm sure there are many friends, there are college students, there are groups who have logged on to this because they know that what is going to be happening today is not only important, but it is extremely rare to be part of something like this. Moving on to tell you a little about the agenda today, because it's very important to tell you what is going to happen. Again, I repeat, if we were in a hall or in an auditorium, the anchor would definitely tell you what is going to happen because you're physically sitting there. Similarly, though this is a Zoom meeting, everybody's time is very precious, and therefore I would tell you what is going to happen today. So we'll be having two sessions for this webinar with a 90-minute presentation by each speaker. The Q&A session will definitely be at the end of the webinar, so stay till the end. Please feel free to ask questions and engage with our speakers. Both of them are also extremely eager for this part because that is what makes the webinar or any knowledge session so enriching and fulfilling for everybody part of this. The target audience, as all of you know today, and I can see it on my screen, is structural engineers, there are architects, researchers professionally right now watching me as I give this preamble. And I'm sure at the end of this session, all of us will go back different individuals because of the knowledge, the experience, the case studies, and everything that has been shared here. Please note that the webinar will be recorded and it will be made available on the Epicons EFC website for future reference. You will, yes, you will also receive a certification, a certificate of participation after the webinar. So friends, this is entirely a very exciting day. And without further ado, let's jump in. The first thing that I'm going to be doing is I have to introduce Engineer Anand Kulkarni. Anand Kulkarni is director of the company since 1992. Again, Anand sir, I think you'll agree with me if I say that the 90s were extremely exciting days for India after the economic liberalization and so many things changed And the first thing to change is the construction industry. So Anand Kulkarni completed his graduation in civil engineering with specialization in structures in 1987. Further, he did his post-graduation studies in structures, and he has professional experience of close to 30 plus years. Of course, involved in design of various type of structures, including residential complexes, high-rise buildings, commercial buildings, institutes, industrial buildings, and so much more. He's, of course, a very important part of Epicons Friends of Concrete. And Anand sir, I'm very happy to have you today. Can you just say a hi to all of us?
Hi, thank you.
Thank you so much.
And good
Yes.
morning, everybody.
Good morning. So, friends, of course, you can see it on the screen, but I always choose to add my own two bit to every introduction. And therefore, something of what I say may not be what is on the screen. Moving on, friends, this is the time when I'm supposed to introduce Dr. Lakshmi Parmeswaran. So just let's wait for 3 seconds to salute not only Dr. Lakshmi Parmeswaran, but all the individuals who are so active in everything that they do. And every single day that they come to office or they go on site, I don't know what's going through their mind, but it is this insane desire to make this world a little better every single day. Apart from this introduction that I'll be sharing with you, I want to narrate a just 5 second interesting trivia. I recently saw a movie called F1, which is about Formula One racing, and there is an engineer there whose main task is to deal with the wind pressure on vehicles that go at 200 miles per hour. And you know what she says to her fellow engineer? She says, if I'm working with the wind, I should be feeling the wind on my body every single day. And Lakshmi ma'am, I think that is exactly what you must be doing when you step out. You're feeling the wind on your face, in your psyche. And what a beautiful coincidence that you're working in the same area. So, friends, to give you a formal introduction, Dr. Lakshmi Parmeswaran is a PhD in civil engineering from IIT Roorkee. That was in 2020, 2002, many decades ago. And in 1985, she did her ME from Coimbatore Institute, has done her BSc in civil engineering in 1984, the rocking 80s. She was the founding chairperson and professor of Engineering Sciences Academy of CSI, of Scientific and Industrial Research. And friends, to sum up this introduction, I would also like to add, particularly one aspect which I simply love is that the kind of research which is required in extremely cutting edge fields like what Dr. Lakshmi Parmeswaran works in also require a huge amount of sensitivity, of knowledge of where the world is going, and of course the core expertise. So on this note, I would formally like to introduce Dr. Lakshmi Parmeswaran, who is Chief Scientist, yes, at CRRI New Delhi. To finish my introduction, I would like to again emphasize that her main interests and work are, of course, in the multiple fields of bridge, aerodynamic wind, effects on structures and bridges, management and assessment and health of bridges, sustainable construction, and so much, much more. Dr. Lakshmi, I'm extremely honored to be the one who has introduced you today. All of us are extremely excited to hear what you have to say, and we are sitting here with bated breath to know every nugget of knowledge that you're giving us. So I hand over to you, Dr. Lakshmi. Thank you again for being here. Over to you.
Thank you, Priyaji. Only one small correction I would like to make that
Yes,
the question answer session will be followed immediately after the lectures.
wonderful. Yes.
Thank you.
Friends, please make a note of that. The Q&A will be immediately after every lecture. That makes it more fun, isn't it? Dr. Lakshmi, over to you.
Good morning, everybody. Thank you, Priya, for the introduction, and thank you, Mr. Jayan Kulkarni, for giving me this opportunity to share my experience with the audience. And I welcome you all to the webinar 149 on design of tall buildings for seismic and wind forces. And the first lecture is on estimation of wind effects on buildings. And as already discussed, the tall buildings are mushrooming and they are essentially designed for dead load, live load, and the main lateral forces like wind and seismic forces. And you can see that they are not isolated structures, but they are not built in isolation, but they are very closely spaced structures. So if some collapse happens for one structure, the other structures are also affected, and also the presence of the nearby structures that is also affecting the behavior of the other structures. So the main forces, the lateral forces for which these structures are designed, that is wind and seismic forces. And we will see the wind action on tall buildings. Basically, you can see that to understand the behavior of tall buildings under wind, we need to understand the wind climate first to a great extent, and then about the structural characteristics. So my first lecture will be focusing on wind characteristics. In fact, you can see that the wind which is always there, and it is affected by the terrain on which the structure is located. And you can see that it is not uniform along the height, but you can see a parabolic variation of wind here. So the wind which is approaching, that is affecting the structure, and depending upon the characteristics of structure, like the structure may be a rigid one or it may be a dynamic one. So the aerodynamic effects also may come into play in some buildings or structures. So basically, when the height of the building increases, like we have to consider the dynamic excitation under the wind effects. And the wind effects typically govern the structural design for strength, stability, and also serviceability. So the first lecture, I'll be covering about the wind characteristics, in which I'll be describing about the wind and the factors which affect the wind speed, like the terrain or topography in which the structure is going to be built. And the wind can come from any direction. So how that wind directionality effect is going to affect the wind forces which are acting on the structure. Then more precisely, it is not a uniform wind, but it is with some turbulence present in it or some fluctuations in it. So how do you define the fluctuations? With the help of turbulence intensity, turbulence scale, and the energy content in the wind, which will be the forcing the structure to the fluid structure interaction. So we will be dealing all these things, and to help the designers, IS 875 Part 3 2015 that has provided how the wind forces can be taken for the actual design of structures. So I'll be introducing you to the IS 875 provisions on estimation of wind effects. When we talk about the wind climate in India, like you can see that they are different from other continents, and wind is nothing but it is flow of air. But how the wind flow is generated, that is because of the atmospheric pressure differentials. But we have to think that the earth is not stationary. It is also rotating. Because of the rotation of the earth, like in the northern hemisphere, the wind get deflected to the right side, and in the southern hemisphere, it get deflected to the left side. So like there are many complexities involved in the wind flow, and we feel extreme winds, and they are like tropical cyclones, extratropical cyclones. Then we have the monsoon wind in our country. Thunderstorms are experienced in many parts of our country, large in number, but for short duration. Then tornadoes are there. Then pressure system wind in very small part of the country. So most part of India, like wind is mix of the above 5 mechanisms, and we have to understand that like what the wind is experienced in Western Europe or Canada, they are different from what we have in our country, because they have more like fully developed pressure system that is there, but we have the extreme events also happening. So our wind climate is different from other countries. So that is one thing we need to understand first. Now coming to the cyclonic storm, actually India has a vast coastal line, and eastern coast, like they have more number of cyclonic storms than the western coast. But nowadays, because of the climate change, the cyclonic storms experienced by the western coast, that is also increasing. Now, let us first understand how these tropical storms are formed. Basically, the high humidity and ocean temperature over 26 degrees, these are the two major contributing factors. Actually, what happens is that the water evaporates from the ocean surface, and that comes to contact with a mass of cold air forming clouds. So you can see the formation of clouds first in the first left-hand side photo. Then the column of that low pressure that develops at the center, which we generally term as eye of the cyclone, and the wind formed around that particular column or around that particular eye. Then as the pressure in the central column weakens, then the speed of the wind around that increases. So that is how the cyclone is formed. And you know that here, this is the eye, and surrounding that eye, like you have the strong winds, and which are having circular contours. So wind moves counterclockwise in the northern hemisphere and clockwise in the southern hemisphere about the center of low pressure. We know that generally, whether it is a wind or it is the water, it flows from high pressure to low pressure. So you have a low pressure here, which we call or eye of the cyclone, and then like you have the circular contours with a high wind there. Coastal regions, they are battered frequently by the severe cyclones, and we have about like 5,770 kilometers of coastline out of a total 7,516 kilometers. That is, that much is prone to cyclone. And why India is prone to this cyclone? Because of its location. You can see that this between this 5 degree to 30 degree, actually above equator, that is in the northern hemisphere, and 5 degree to 30 degree in the southern hemisphere, like that region that experiences more cyclone. So totally like you have something like 80 to 90 cyclones every year globally, and 45% of that is in the northeastern hemisphere where India is located. So that is why like we experiences the cyclones every year. Now we have to understand that the cyclone, it is not an independent phenomena, but it is accompanied by flood and also storm surge. And another important aspect is that we have already seen that there is a formation of the heavy cloud and also the rain happening along with that. So if you see the center or the eye, then the eye wall that has a diameter of about, that has a radius of about 20 to 30 kilometers, and the region B, that is 30 to 50 kilometer. So there, like you find that that particular region, that is 30 to 50 kilometer radius from the center, that experiences more heavy clouds, rain or updraft. And also, like the cyclone has a circumferential wind speed variation, because when we talk about the wind, we always talk about the variation of wind speed with respect to the height. But we have to understand that in the case of cyclone, there is a circumferential wind speed variation, and that can be felt up to an area of up to a radius of 300 to 600 kilometer. So this aspect also we need to think about, and also to cater how this has been catered in IS 875. That is also another important aspect. If you see the wind and cyclone map of India provided by NDMA, you can see that, like, we know that there are different wind speed zone, that is basic wind speed varying from 33 to 55 meter per second. But you can see that number of cyclones, like in the eastern coast, like they are on the higher side. And when we call a wind as a tropical cyclone, that is when the wind exceeds the gale force, or you can say that at least 63 kilometer per hour speed is there, then we call it is a cyclone. And already discussed that the cyclones, they are associated with the high wind speed and also storm surges and also exceptional rainfall occurrences, which can lead to some floods also. So when we talk about the categories of cyclones, like you can see, we generally hear the term depression. That is, a depression has developed either in the Indian Ocean or Arabian Sea, like that. So there you can see that 31 to 49 kilometer per hour, that is moderate to rough condition of the sea, where you have the wave height likely to be there between 1.25 to 2.5 for moderate and 2.5 to 4 meter for the rough sea. Then deep depression, that is 50 to 61 kilometer per hour, where the wave height may be up 4 to 6 meter. Then cyclonic storm, that is 62 to 87 kilometer per hour, where the wave height may be 6 to 9, and the condition of the sea will be quite rough. And severe cyclonic storm, and again you can see that the wave height is increasing to 9 to 14 meter. Then very severe cyclonic storm and super cyclonic storm, because these are basically phenomenal, not always happening, but maybe once in a while. But if the wind speed is exceeding, then you just think what type of devastation it is going to cause. And the wave height is also 14 meter. Then we have more short thunderstorm experiencing in many parts of our country. That is another type of, like you can say, strong wind. And tornado, that is a narrow band phenomena. In fact, yesterday in US, like they had one tornado happening there. And they are basically an inland activity covering comparatively small area, but tornado generates high tangential wind velocity, and it is also accompanied with substantially potent updraft and radial velocities. That means like the variation of wind speed in this event is also different from the normal wind. So the windstorm, like the scales and effect, they are expressed like with the help of this Beaufort scale. And you can see that there are 0 to 12, and 12 is the hurricane here, and which has more than 32.7 meter per second or 64 knots more than that wind speed is there. And this wind speed is 10 meter above the surface. And then like we have the Saffir-Simpson hurricane scale, because the cyclone that is known as hurricane in US, and they have classified that into weak to devastating hurricane, and there the wind speed is increasing to more than 250 kilometer per hour. And there is another Fujita tornado scale. Again, they are depending upon the wind speed, like that is classified from weak to disaster scale, and the wind speed is increasing to 136.9 meter per second. So these are basically how you can classify the cyclonic storm or like the tornado based on the wind speed, and definitely that will be associated with what type of devastation it causes. So for example, the damage is expected, especially with respect to buildings, as stated by NDMA, is that if it is a deep depression or a cyclonic storm, actually that is likely to cause a major problem, you can say, to the loose and unsecured structure or some thatched huts which are there in our coastal area, like that they are the first one to get damaged. Then with severe cyclonic storm, again damage to the thatched huts. And it is not only that they are going to affect only the huts or the buildings, but along with that, there may be uprooting of trees or the damage to the power and communication lines, or it may affecting the electric poles and also like other structures. Then very severe cyclonic storm, extensive damage to the thatched roofs and huts. Very severe cyclonic storm, again they can damage some old buildings, large scale disruption of power and communication line, and super cyclone like the one which we experienced in Orissa. There, like you can see that structural damage to residential and industrial buildings, and total disruption of communication and power supply. In fact, after the Orissa cyclone, Ministry of Communication, they decided to design the communication towers for a very high wind speed because they want the communication towers are also essential for post-disaster activities. So they don't want the towers to get damaged because of the high wind. So now coming to the design of structures for wind effects, basically, like though we have seen that there are various extreme events happening, but the design of structures for wind effect, that is based on basically the boundary layer flow, So we will be focusing on what is boundary layer flow, and though it covers the cyclonic storms, but not tornadoes and thunderstorms, but we will be focusing now on the boundary layer flow. So for that, like we need to understand about the wind. Basically, as I said, that the wind velocity, that is not constant over time. Actually, it is a time varying phenomena. It is a space varying phenomena, and also along the height, the wind speed is changing. So you can see here that there is a mean component and also there is a fluctuating component. That is, wind is a random phenomena, and it has both time, it is a time varying phenomena, and mean component is also there, and a fluctuating component given by this mean component given by V bar and fluctuating component given by V dash. And if you see the this particular figure, you can see that at the ground zero point, like you can see that the wind speed is 0, but it increases like in a parabolic manner, and that is along the height it is going to increase. But if you see the turbulence, the fluctuating component, it is more near the ground, but that is going to decrease along the height. That means the variation of wind velocity is there with respect to time and with respect to height also, but we have to understand that the gustiness is more near the ground, but when you go higher, then the gustiness is going to come down. So this is called the boundary layer wind. And how do we express this wind mathematically? Basically, there are two means by which like we can describe the mean wind profile in atmospheric boundary layer. One is the logarithmic law or log law, which we call, and which is included in IS 875 part 3 to describe the wind profile along the height. And the second one is the power law. So I'll be discussing about these two first. That is, if you see that V bar Z, that is the hourly wind speed at height Z, then that is a function of friction velocity, and then one von Karman constant, which we generally take as 0.4, and then logarithmic of Z, that is, it varies with height. So at any height Z, and Z0, that is the surface roughness length of the terrain. Surface roughness length means like that surface which is offering some resistance to the flow of wind, that we call the surface roughness. So this is the logarithmic law which is used to describe the mean speed along the atmospheric boundary layer. And another is the power law that may be used to describe the ABL. In fact, this is important because if you see any of the wind tunnel test report, there the wind law, the wind in the simulated in the wind tunnel, that will be based on the power law. So here you can see that the referent wind speed, that is a function of like the speed at the reference height. Generally, we have 10 meter taken as the reference height. So at any height Z, maybe 20 meter, 30 meter, and that divided by, that is, if it is a 30 meter height we want to compute, so 30 by 10, and there is an exponent here which we call the power law exponent for the terrain roughness. So here the power law, there is an power law exponent which is corresponding to the surface roughness or the terrain roughness. Now, one thing we need to understand that when we are talking about either the hourly mean wind speed, like there is no gust wind included. But if we want to find out from the hourly mean wind speed, means what I want to say is that either the log profile or the power law profile, they are basically the mean wind speed profile and not the gust speed profile. But if we want to get the gust speed profile, then we need to include two terms. That is, one is the peak factor for upwind velocity fluctuation and another is the turbulence intensity. So about these two, we will be looking more in detail in the coming slides. So first we need to understand about how the terrain and topography is going to affect the wind speed. And we know that the terrain on which the wind is flowing, that is also not constant. So the structure may be like located like very close to the sea, that is on the coastal region. So you can see that there like very little resistance is offered by the water. So you can see that at a particular height, like you can see something like 0.8 Vg. Vg is the gradient velocity. That is, after it reaches this level, there is no variation in the wind speed. So we call the gradient wind velocity. So it may be something like 0.8. But you can see that there are many trees, windward coast, there are many trees, etc. So that means the trees are offering resistance to the flow of wind. So at a particular, the same height, if you see, this 0.8 G has become 0.6 Vg. That means these trees are offering some resistance. That is what I say, that the terrain roughness is created by the presence of these trees. Now, there is a hill there. So that means there is some sort of an acceleration of the wind speed happening. So if you have a structure here, that will be experiencing not 0.8 Vg, but something like 1.2 Vg. That means there is an acceleration of wind when it comes to the top of the hill. But on the downside of the hill, if you see that the profile is somewhat different, why this difference is happening is because this hill is basically sheltering the structures which are there on the down hill side. So you can see that here not 0.8 Vg is happening, but what is experienced by a structure here is only 0.4 Vg. So this basically explains how the terrain and topography is presence of your hill, valley or ridge, etc. So that how that is affecting the wind speed. Again, like you can see that like this is the mean wind flow here, which is VMF, that is at a height is at about the terrain, but you have a hill here, and when it is here, it is on the higher side. That is, it is VM. So VM by VMF. So you will get how much it is going to increase. So while citing the buildings, what we have to remember is that like the trees basically, they shield the high wind, the structure from high wind, and also the hillock, they also protect the buildings on the downhill side. But if you are constructing on top of a hill or a ridge, like then that will be subjected to higher wind velocities. So the downhill wind that is going to get protected. The downhill structures are going to get protected from high wind velocity because there is a sheltering effect here. And as we discussed that the cyclonic events, they are accompanied by rainfall and flood. So it is better that we don't construct at low level, but better to construct it on artificially raised earth mound, or maybe a little above the ground. If we construct, that will protect it from the flood also. Now, like, we need to understand about the macro and micro meteorological peaks. So we can see here that this is the power spectral density or the energy content in the wind. And you can see here that there is first the macro meteorological peak, which is on a higher level compared to the micro meteorological peak. And you can see that the frequency is given in the x-axis and the power spectral density is given in the y-axis, which is nothing but the energy present in the wind. And you can see that from the x-axis, this is basically the low frequency range here, which is associated with fully developed weather system. Okay. And then the micro meteorological peak, which is on the, you can say that high frequency level, but there, that is, the fluctuations are generated by the stirring of the mean flow by surface friction, like the terrain roughness, which we discussed. So the turbulence in the boundary layer, that is causing this micro meteorological peak. But the macro meteorological peak, that is associated with some pressure system, or you can say that weather pattern like monsoon, cyclone, etc. So if you are planning to go for some wind farm or like wind power generation, which are the positive effect of wind, then you consider this macro meteorological peak. But when we talk about the design of structures, basically the frequency range of the structure generated turbulence, what we consider, that is the micro meteorological peak. And in between the macro meteorological peak and micro meteorological peak, we see a spectral gap. You can see that this 1 hour or 10 minutes there, like you can see that not much disturbance is there, or the turbulence or wind fluctuations are found to be insignificant at this particular frequency values here. And even here, not much fluctuation is there. In fact, like if you talk about the wind, the averaging speed of wind, that is important for the design. And many codes, like for example, IS 875 part 3, it gives 3 second average wind speed. Then like it has 1 hour hourly mean wind speed description also. And some countries, they follow the 10-minute averaging time for the wind. But you have to understand that like the spectral gap is where the fluctuations are insignificant, and macro meteorological peak, that is associated with a fully developed weather system, whereas the micro meteorological peak, which is important, the energy content of that is very important for the design of our structures. Now coming to like how these terrains have been classified in IS 875, you can see here that there are 4 categories: TC1, TC2, TC3 and TC4. Basically, the first one is open sea coast or flat plain, where like the object's heights are less than 1.5 meter and the surface roughness height, that is something like 0.002 meter. and the TC2 category, that is corresponding to undeveloped or sparsely built up outskirts of town and suburbs, where you have well scattered obstructions having height generally between 1.5 and 10 meter, and the surface roughness height is 0.02 meter. And third category, TC3, that is well wooded area, and there the surface roughness height is 0.2 meter. And TC4 is the large city center, like the urban centers, where the surface roughness height is 2 meter. So this is the category how IS 875 has classified. And as I said, this open sea, open level country, suburb, forest and city centers. So these are the boundary level height, because this boundary layer height also increases with respect to the increase in the terrain roughness. And as I said that the wind tunnel, we will be simulating the wind using the power law. So these are the typical power law coefficients like 0.14 to 0.4 as the terrain category increases. And also the height is also important, because depending on the height of the structure, like the height, that tall structure, that or whatever structure is there, that has to be within this particular boundary layer also. So basically the boundary layer, the atmospheric boundary layer, within that boundary layer, the gustiness of the wind that is arising because of the frictional interaction with surface features such as vegetation, building or water surface, which we call it as terrain. I hope it is clear that we are talking about the boundary layer and how the wind speed is varying with different terrain roughness, and how that can be mathematically expressed like using the log law and the power law. So now coming more in detail about IS 875 Part 3 2015 provisions, like we have basically the wind map provided, and this wind map is based on the IMD data, where they have the wind measurement done in various parts of our country. So that height is measured at 10 meter above the ground level. And what we have is a wind which is average peak gust velocity averaged over short time interval of 3 seconds, and it corresponds to open terrain, that is category 2, terrain category 2, and also it has a return period, that is 1 in 50 return, the probability of return of having a wind, that is 1 in 50. So you can see that there are 6 zones here, that is 33 meter, 39 meter per second, 44 meter per second, 47 meter per second, 50 meter per second, and 55 meter per second, which are demarcated in this wind map of India with different colors. So the first thing when you are going to design, you need to understand where your structure is going to be located, and you have to select the basic wind speed for that particular location. So from the basic wind speed, then we come to the design wind speed. So the design wind speed is going to get affected by the risk level, terrain roughness and height of the structure, like we discussed about the atmospheric boundary layer and how the parabolic variation of wind is happening. So how that is included in IS 875, and then the local topography like the hill, etc. Then there is a factor that has been included in IS 875 Part 3 to consider the cyclonic wind effects. So mathematically, it is expressed as VZ. Z is the height above the ground level. So that is that can be obtained from the basic wind speed by multiplying the basic wind speed with K1, K2, K3, and K4, these four multiplying factors. So K1 is the probability factor or the risk coefficient, and K2 is the terrain roughness and height factor, and K3 is the topographic factor, and K4 is the importance factor for cyclonic region. So basically, like if your structure is less than 10 meter, then you take that as a 10 meter high, and it can be reduced by 20% for evaluating the stability and design of framing. So this is the same thing, like the design wind speed is obtained from the basic wind speed by multiplying with K1, K2, K3, and K4. So now coming to the K1 coefficient, you can see that that is depend on what is the mean probable design life of structure. You can see that all general buildings, like we have 50 year, and you can see that K1 factor remain constant of 1 across the wind speed zones, and temporary sheds, etc., like the mean probable design life is 5. So the factors are varying from 0.82 to 0.67. Then the building and structures presenting low degree of hazard, there it is 25. And again, the factors are varying. And important buildings and structures, they have higher design life, like 100 year. So you have a factor which is more than 1, varying from 1.05 to 1.08, depending upon where the structure is located. So these factors are given in this particular table. And also, like if you want to work out like the K1 factor for any other return period, like that also a formula is given here. So basically, that formula helps to find out if it is for 10 year or 20 year, like you can work out what is the K1 factor. Now comes the terrain and height factor, basically the K2 multiplier. Again, you can see that like the terrain one is a open terrain with very little obstruction. So you have even a multiplying factor on a higher side compared to TC4, which is a urban center or a city center. So here it is 1.05. That is at 10 meter, the wind speed will be higher like an open sea, or it will be much lower in a city center. And TC2, you have a value of 1, because we said that the basic wind speed map has been prepared corresponding to terrain category 2. So you have for other terrain category, there is a multiplying factor, and the factor is more than 1 for TC1 and lower than 1 for TC3 and TC4 at height up to a height of 10 meter. And the values are given up to 500 meter. So if you want to design a structure up to 500 meter, this can be used for that. Now, as I said that there are two averaging wind speed given. One is corresponding to 3-second gust. That is the basic map, wind map, which is based on. And another is the hourly mean wind speed, where the averaging time of wind is 1 hour. So there, instead of that K2, like you have a different multiplier that is called K2 bar. And how this K2 bar is coming, there is an equation given here. And you can work out that, or this is the table which gives the hourly, K2 bar multiplier, or the terrain and height multiplier for like the hourly mean wind speed computation. So here you can see again that for the TC1 for 10 meter, the factor is 0.78, whereas for TC4 the factor is 0.82. 24. So again, the K2 bar factor is given from up to 10 meter to 500 meter in this particular table. Now, another factor, that is the topography factor. So as we discussed that the basic wind speed that is given for like general level of sight above the sea level, but there is, suppose there is a hill or some topographic feature is there, then there will be some acceleration of wind speed near the summit of hills or crest of cliffs, etc. So how to work out that K3? So that is also included. In fact, the up to 3-degree slope, the upwind slope up to 3-degree, like the multiplication factor is 1 only, but when it increases, then the factor goes between, varies from 1 to 1.36. So how it can be worked out, that is given in the appendix C of IS 875 part 3. And you can see that first we need to understand how much length is affected by the topographical features. So to obtain the effective height of topographic feature, like that is between 3 to 17-degree upwind slope, the effective length is taken as L, and for more than 17-degree upwind slope, it is taken as Z by 0.3. So here the topography factor can be computed as 1 plus C S0. So C, how it can be taken for different slope, that is given in this particular slide, and how to take the S0, that is given here. So you can find out what is the S0 to be taken if it is on the crest, or like if it is on cliff and escarpment, that is given in this particular figure. That is figure 14 for the factor S0 for ridge and hill, and factor 15 for cliff and escarpment. So depending on where your structure is located and what is the length influenced by that particular topographical feature, one can work out the K3 factor. So appendix C of IS 875 gives that. Now, like there is an importance factor for cyclonic region, that is K4. We have seen the structure of the cyclonic storm, and we found that up to like 50 kilometer, like you can see that effect is much more, and also there is a circumferential variation of the wind speed is also there. So, as I said earlier, that our east coast of India, that is more vulnerable to occurrence of severe cyclones, but on the western coast, like the Gujarat coast, that has also severe cyclones. And because of the cyclone, like
Sorry to interrupt. All participants are requested to mute.
Cyclones, they are damaging, causing damage to the building and structures. So the effect of cyclonic storm is largely felt in a belt of 60 kilometer width at the coast. So there is one IS standard, that is IS 15498.
Admin, please mute.
Can you please mute? So the IS 15498 that is guidelines for improving the cyclonic resistance of low-rise houses and other buildings and structures. So they have given the multiplier factor for the K4 factor. So that has been included in IS 875 Part 3. So for structures of post-cyclone importance for emergency services like hospital, school, communication tower, etc., we have a higher multiplying factor which is more than 1, that is 1.3. And for industrial structures, there it is 1.15, and all other structures we take as 1. So this is the importance factor for cyclonic region. Now, what to do with the design wind speed? Actually, that is used in the calculation of design wind pressure. So again, if you have a peak gust wind speed, then you can compute the design wind pressure, half rho v square. So that is 0.6 VZ d square. And if it is an hourly mean wind speed, then you get the hourly mean wind pressure at any particular height. So it is used to find out what is the pressure from the wind speed. So it is used for that calculation. Now I will discuss about the turbulence intensity. As I said that there are 4 terrain categories, and for these terrain category, we said that the roughness will be, the turbulence will be more near the ground, and it reduces with respect to the height. And again, it is a function of the surface roughness height. So you have these 4 equations, and for convenience of the participants, I have prepared a table. So you can take the terrain and turbulent intensity from this particular table, and you can see that for terrain category 1, it varies from 0.15 at 10 meter to 0.06 at 500 meter. And whereas if you see that terrain category 2 has more turbulence intensity at 10 meter height, and maximum is for TC4, which is 0.37, but along the height again it is falling down to 0.14. So this is the variation of turbulence intensity. Now coming to after discussing about the wind speed, design wind speed, and the design wind pressure, like we will just see how it is going to affect the building. So building again, we have the low-rise building, and we have seen that large number of these low-rise buildings are getting affected by the cyclonic winds, etc. So they are the vulnerable components which are prone to wind action is the wall, roof, and then the walls, they have certain openings like door, window, etc. So the opening on wall and secondary members of the roof, that is which is supporting the roof material, then how the connection between the wall and roof is there, or the connection between the roofing material and the supporting members. So these are all affected by the wind forces. So when we talk about the wind acting on low-rise building, you can see that it is having a positive pressure on the front wall on which it is acting. Then what happens? There is an uplift on the roof. There is a suction, that is the force which is moving away from the side wall, or from there is again a suction on rear wall, or the force which is moving away from the rear wall. The positive pressure means it is acting on the wall, and suction means it is moving away from the wall. So these are the forces which are acting, that is wind interact with a structure. The pressure and forces on the surfaces of the wall and roof, they are generated, and the characteristic of this pressure, that is influenced by the approaching wind characteristics as well as the geometry of the structure. So with respect to the wind action, it is the geometry in plan and elevation that is going to be very, very important. So significant internal pressure that develops because the buildings invariably they have openings like door, window, etc. So where the openings are there and what is the permeability, so that is also going to play an important role. That means the geometry, shape in plan and elevation, and where the openings are there, and that will cause the internal pressure distribution, and wind while moving around that particular structure, that will cause pressure on some walls and suction on other walls, and also it can cause an uplift on the roof. So this is the flow separation, because we need to understand the flow separation pattern. So for example, this is a roof and this is the boundary layer profile, and you can see that the wind is attacking this particular wall or impinging on this particular wall, and this is the stagnation point. And beyond that, what happens is that it separates from one of these corners, and you can see that some eddies are also formed, and depending upon the size of the building, it may get reattached like this. And once it is reattached, again, it may get separated like this, and some shear layer is formed. So the point of, you can say, the attachment and separation, that depends on the size of the building. So that is, the flow is getting attached and separated, and a shear layer is also formed. So the wind effect on buildings with different shape of roof. You can see that here the gable-ended roof, they are subjected to high uplift. Okay, but when the shape of the roof is changed to hip roof, they get lower uplift. And when you have a pyramidal roof, then that has the lowest uplift. So what you can do is you can select a particular shape of the roof which will provide least uplift. So that will be beneficial for you for your design. And if you have a flat roof, then the wind pattern, if it is a uniform flow, you will get a pattern like this. Again, you can see that this is the separation point here. But if it is a boundary layer flow, what happens is that, like, there is a separation and then there is a reattachment. So if you have a, why I am showing this particular figure is that, like, the wind flow is not a uniform flow, but it is a boundary layer flow. And but IS 875 that has given the pressure coefficients. Many of them are the pressure coefficients obtained on models which are tested in uniform wind flow. So that may be on, you can say the values may be something like the pressure coefficient like 0.6, etc. But here the average value will be 0.2, etc. here. So the if it is subjected to a uniform flow, the pressure distribution is somewhat different. And if it is a boundary layer wind flow, the pressure distribution is different. And basically the weight of this particular object, that will decide how much drag or wind force this particular structure is subjected to. And we can obtain the compute the drag and lift forces by integrating the pressure which are generated around the surface. So the pressures on structures, they are not steady, but highly fluctuating. And why they are fluctuating? Because the approaching wind itself is also fluctuating. And also there are local eddies which are generated because of this separation, reattachment, again separation, etc. So what we need to understand that the pressures are not uniformly distributed spatially over the surface of a structure. They are not uniform. Okay, so that means the wind itself is a time varying phenomena. It has the fluctuation. It is varying spatially. It is varying along the height. And when it is impinging on a particular structure, the pressure distribution around that body, that is also not uniform. So the wind pressure and force on the building, like IS 875, that has given how it can be calculated for building as a whole, or like for individual elements like roof, wall, etc. And another is the cladding units like glazing or the connections which we discussed, that is the fixings. So here, after we compute the design wind pressure, like there are certain multiplication factor given here. One is the wind directionality factor, another is the area averaging factor, and another is a combination factor. But there is also one rider, that the value of PD, that the design wind pressure, that shall not be less than 0.7 PZ. So that is what they give. So now we try to understand what is the wind directionality factor, because the wind direction again, that can be random. So considering the randomness in the directionality of the wind, and because if you see the IS 875 pressure coefficients which are given, we can see that like they are given at different wind angles, they are given. So, but the wind need not be coming depending upon the location of the structure, like the direction will be changing. So it need not be the peak always. So there is a multiplication factor of 0.9 that has been given for certain type of structures. Then again, like what is the averaging factor? So that depends on the area on which the pressure is acting. So if the tributary area is lower than 10, then there is an averaging factor of 1. But if the averaging area is more, then the averaging factor is 0.8. And also, like the combination factor, that is the for a as I said, that the openings also creates a fluctuation in the wind speed. So maybe the roof is subjected to, you can say, an uplift, but the internal pressure that may be acting on the surface. So maybe some pressure is there. So to consider these complexities, like there is another combination factor that is given, and that factor is something like 0.9. So this is how like the design wind pressure is going to get modified depending upon the wind directionality aspect, and also the area on which the pressure is going to act, and also the combination factor, a reduction factor has given. So when we talk about the individual members like wall or like roof, etc., they are both external pressure coefficient and internal pressure coefficients. They are given, and area is the surface area on which the pressure is acting, and PD is nothing but the design wind pressure. And as discussed in the previous slide, that has been slightly improved, taking into account these factors. Then for individual buildings, like we can have like the force coefficient, that is by integrating the pressure which is acting on various elements, like we get the force coefficient. So the force acting on a building as a whole, that can be obtained by multiplying CF, nothing but the force coefficient, then the area, the frontal area, because whenever like we think about wind, we think surface on which the wind pressure is acting on. So that is the frontal area on which that pressure is acting on, and then the design wind pressure. So we can work out the force acting on a building. And suppose you have a tapered building, because generally like tall buildings, like you may be having a wide bottom and narrow top. So you can divide the structure into different strips, and for each strip, like you can work out what is the fin force acting on a particular strip by considering that that particular area of that particular strip. Now the question is, what is the force coefficient to be taken for a building? For a rectangular clad building, like the force coefficient has been given in IS 875. And you can see that again, it depends on the plan area, that is the plan dimension, that is A and B, the plan dimension of that particular building, and also the height of the building. So you can see here that depending upon the A by B ratio, you can work out, you can take the appropriate force coefficient corresponding to an H by B factor. So these are the force coefficient of the rectangular building in the uniform flow. So these factors can be taken for considering the pressure computation. And also, like apart from the rectangular shape, there are also tables corresponding to various other shapes. Again, there also like the H by B factor that is important, and A by B that is important. So those things are given. So what I want to tell you is that like you can use IS 875 to work out what is the pressure which is acting on various elements like roof, wall, and where there is an opening, there is an internal pressure coefficient, and otherwise on these components, the external pressure coefficient. Then when you are considering building as a whole, then you have the force coefficients which are also included in IS 875. So once you compute the design wind pressure, then you can work out the force which is acting on the building as a whole. Like if you know the force coefficient for that particular building. But you have to remember that the values which are given in IS 875, they are all based on like internal studies, but some of the internal studies, they are on like you can say uniform flow, and some of them in boundary layer flow also. And if the shapes are something different, then what is shape of the building is something which is different that what is given in IS 875, then you may have to go for some specialist literature, or you may have to go for some internal studies to obtain those force coefficients or the pressure coefficients, etc. So we will be looking these aspects more in the next lecture. So if you have any question, then we can have a discussion here.
Okay, thank you, Lakshmi Madam. You have made the subject very simple for the viewers. Very well explained the wind characteristics and structural characteristics. We move on to few questions. The first question is for coastal areas, residential tall buildings, K4 factor, should it be 1.3 or 1?
Coastal area within 60 kilometer, like it is better to take it 1.3.
Okay. As then the
Shall I
next question.
stop share, or
Yeah. Okay, so the next question is, as I observed, wind load calculation method is Eurocode and IS code is different. In Eurocode, for example, for a water tank staging, the load calculation is in detail. but in IS code method is very simplified. Why this different method of calculation between IS and Eurocode? It's particularly talking about water tank staging.
Water tank staging, again, like you can see the dynamic characteristics, etc., may be coming into picture, and also the water tank may be full, water tank may be empty, and also the height of the staging may be different. But if I see that, like some earlier in IS 875 Part 3 1987, there again, like an explanatory handbook was prepared by BAS at that time, and that was giving some examples at that time. But 2015, I'm not sure whether any explanatory handbook has been prepared, but those things can be worked out based on structural principles.
Right. Okay, so we move on to the next question. What is the criteria of selection of 3-second versus hourly mean gust?
See, hourly wind speed that we have to consider for the dynamically sensitive structures, which I will be talking more about in the next lecture. And other structures, we can take the 3-second gust. Actually, there the gustiness is already included there. But if you are using an hourly mean wind speed, that is, suppose you have a short averaging time, then any randomly varying phenomena, when the averaging time is less, that will result in a higher value. But if you have a long averaging time like 1 hour, then the value will be on the lower side. So there, like the gustiness or the gust factor, that has to be included in computing the wind forces. So like 3-second gust is there, because that is more simple to adopt. But if you want to have an hourly mean wind speed, then the gust factor also to be computed. Again, the gust factor has other components like background factor and then the resonance factor, etc. So for more dynamically sensitive structure, we prefer hourly mean wind speed, and other structures like your low-rise building, etc., we go for like the 3-second peak gust.
Yeah. Okay, so the next question is K2 bar for hourly mean wind speed is given only for category 1. Is it same for all categories?
No, actually, like if you see that there are 4 equations given in IS 875 Part 3, and they are based on the, you can say from terrain category 1, the other things can be computed. So that's why in my lecture, like I have given a slide where I have worked out the turbulent intensity factor for all other terrain categories also. Otherwise, like you can use it, use those equations to compute the terrain turbulent intensity if you know the surface roughness of various terrain categories. Yes, yes.
Okay, so the next question is, as the code for external pressure coefficients can be obtained from table 5 or clause 7.4.2, can you please clarify the difference between the two? Can both be used for calculation to calculate external coefficient?
The question is not clear to me.
Yeah, question probably means the table 5 gives pressure coefficients, and clause 7.4.2 also gives some way of calculation of pressure coefficients. So is there any difference between the two? But I don't think so there any difference. We can apply this clause and just check the results from the table 5. We move on to the next question. How significant, how is stagnant point location with respect to height of the building?
Stagnant point location with respect to height.
Yes, stagnant point location with respect to height of the building. I don't also understand what does he mean by the stagnant point.
I think we should not worry about the stagnant point, but we should more worry about where the flow separation is happening and where the reattachment is happening. So the corners are one point where the separation happens, and depending upon the size, the reattachment happens. Because when the flow separates, then the eddies are generated. So we, as a structural engineer, we should worry about the separation and reattachment point rather than the stagnation point. That would
Yeah.
that will be my answer.
Yeah, so we should follow the wind path and the effects of the wind on the roof. So the next question is, as per IS 875 Part 3 2015 Table 5, the building facade corner region is defined as 0.25, whereas Table 6 indicates corner region for roof is 0.50. Kindly explain.
I think this question probably has to be seen with respect to the code, what the values given. Basically, in the code, there are mean pressure zone and the local pressure zones they are given. So that is basically given because you don't generally design it for the peak, but the connections can be made more stronger in the local pressure region where like you can have there is a possibility of uplift there. So with respect to that, like they have divided the roof into different zones, and the pressure coefficients which are obtained from the internal studies, they are given. And again, like the directionality effect also is included because you have the pressure coefficients obtained from the internal studies by changing the wind direction of the structure that is given in the code.
Correct. Okay, the next question is IS 875 wind pressure reflects the before scale.
See, the Beaufort scale is basically a scale to categorize the wind phenomena and also how much speed is coming. Corresponding to that, how that is felt by the people or the structures, etc., to connect the wind speed with respect to the damage experience by the structure or people. Maybe in some speed, like you find difficulty in walking, or maybe the trees are getting uprooted, etc. So it is for connecting that.
Yeah, right. So basically, you can correlate it with the Richter scale. We directly don't design it for the Richter scale. However,
Yes,
that's
yes,
a measure of the
yes.
magnitude of that.
Yeah,
So
yes.
the next question is how force coefficient are obtained for circular, elliptical, or undefined geometrical shape of a building?
See, circular geometry, like again, like it is given in IS 875 Part 3, only thing you have to think that for circular structure, it varies with the Reynolds number also. So
Right.
that is given in IS 875. And elliptical, again, the shape that is given, there are 3 tables given. One table given in 3 pages, like that for the elliptical shape, like how the force coefficient can be obtained. But if it is a shape which is not covered in IS 875, then you have to obtain it like from internal studies or by computational fluid dynamics,
Right.
which I'll be discussing more in detail in the second part of my lecture.
Yeah. So there are many questions coming up, but we'll take last 3 questions and maybe remaining questions we can take during the next session. How to consider vortex wind effects and any tips to consider dynamic wind analysis?
Yeah,
Consider
that will be covered in the next lecture.
Yes,
Next
right.
lecture. Yes.
What is the difference between pressure coefficient and force coefficient? Why we
See,
are using CF in the place of CP in wind load pattern in ETAPS?
actually, as I said that, like in the case of low-rise building, basically the wall and the roofs, etc., they have to be designed, and there the pressure which is acting on the surface, that is the important parameters. So we are considering there. But when you are talking about a tall building, there like you are considering the base moment and shear, etc. So there the force coefficient has to be taken, and force coefficient is nothing but that is an integration of the pressure coefficient. That is how you get the force coefficient. So from the pressure coefficient only we are getting the force coefficient. Okay, so it all depends on which component you are designing or the building as a whole you are designing. So if you are designing the component, go for the pressure coefficient.
Okay. There's one question. For tall structure, usually certain floors are kept open without cladding. How does this pressure profile gives an advantage to the structure?
Yeah, that is some openings are provided because that will ease the wind to flow from one direction to another. Because if you see that even the frame structure, like the solidity ratio, depending upon the solidity ratio, like the force coefficients are changing. So again, that helps, and that is also one means by which like you can make the wind forces on the lower side. So I'll be discussing more about the aerodynamic modification in my second lecture.
Okay. The last question, the across wind limited, for across wind calculation, limited graphs are provided for selective ratio of building.
Yes.
What if the ratio doesn't match with the graphs provided?
Yes, this point I'll be discussing in the afternoon lecture. But if it is not matching, then it is better like you go for some specialist literature or go for some internal study.
Okay, I think we are finished with
Okay.
the important questions.
Yes.
And over to you, Priya Madam, for
Right.
that. I think, yeah. Thank you.
Thank you, Anand sir, and thank you, Dr. Lakshmi. We are, of course, joining and meeting you in the second half. But what an amazing talk this has been. And I love the way you started with those currents and cyclone. It makes you want to know so many other things apart from the technical part of this also. And I thoroughly enjoyed this, and I'm sure everybody has. Moving on to our next speaker, but before that, I would like to introduce to the gathering Engineer Arvind Parurekar, and we shall soon see his bio on the screen. Arvind Parurekar is, of course, an MTech from 1990 from MS University, Baroda. He serves as the director of the company, that's Epicons, since 1999, a part of the top management of the company, very involved not only in the day-to-day management of both the verticals of the company, which is Structural Design Unit 2, handling structural design projects with specialized scope, and also the NDT, which handles the assignments related to, as all of us know, structural assessment of existing structures using various techniques, including NDT. His expertise includes structural assessment of existing structures, including seismic evaluation, analysis of NDT results, design of strengthening and retrofitting measures, and analysis of structures with special features. Of course, Parurekar sir is a member of Institute of Engineers as well as a life member of Indian Society of Structural Engineers. A licensed practicing engineer for many, many years, Parurekar sir is, of course, I don't need to add a very, very important part of all the webinars that you have been seeing happening from the house and the platform of Epicons. So Arvind Parurekar sir, so happy to meet you once again at an amazing webinar and very happy to be here with you.
Thanks,
Of
Priya.
course, now is the time when I shall be introducing our guest, our second speaker for today, Professor Dr. Yogendra Singh. Before I formally introduce him, I would like to humbly say that I recently read a quote by American journalist Charles Kuralt. I'm not sure how his surname is pronounced, where he says in a rather sardonic manner that it takes an earthquake to remind us that we are walking on the crust of an unfinished planet. I mean, how profound is this statement, isn't it? And that's where we come to this field of earthquake design where we already know so much and we already do not know so much. Which brings me to the great honor of introducing Dr. Yogendra Singh, a professor, former head Department of the Earthquake Engineering at IIT Roorkee, a civil engineering graduate from 1989, did his MTech and PhD from the same institute as alma mater, IIT, in the years 1990 and 1994 respectively. He's hugely interested in very cutting edge fields like performance based design of buildings and bridges, seismic vulnerability and risk evaluation, and earthquake engineering in the hilly regions. More than 30 years of deep research and teaching experience, served 2 terms of Indian Railway Bridge Engineering Chair, has supervised 20 PhD, maybe now more, who have published more than 100 research articles in journals, and he has presented more than 120, maybe so many more, papers in conferences across the world. He is also interestingly reviewed for a number of journals and serves on the editorial board of the Canadian Journal of Civil Engineering. Yogendra sir has also been member of several teams for the post-earthquake damage management surveys, which, as all of us know, are very important to assess what is to be done the next time nature wreaks her havoc on this unsuspecting world. As a convener of not only the BICD 39 working group for drafting the Indian standard on performance-based seismic design of structures, but Yogendra sir has also been the convener and been a very important part of so many conferences, webinars, major discussions on this extremely important topic. Lastly, I would like to add that he has a significant contribution in seismic safety of infrastructural projects in the Indian Himalayas, which all of us knows is a fragile ecosystem, and we all want to protect what we have, isn't it? So, Yogendra Singh sir, so happy to be the one to introduce you. I hope I have done a satisfactory job in introducing both Dr. Lakshmi and yourself. Please go ahead. Over to you.
Thank you, Priya Madam. Yeah, you have done a wonderful job. Thank you so much for this nice introduction. And good morning. I hope I'm audible, and
Yes, sir, you
I
are.
will share my screen.
And meanwhile, sir, I forgot to mention the official title of your presentation, which is Seismic Hazard and Estimation of Earthquake Forces on Building, Changes in the Revised Codes. Over to you.
Okay, so I think my screen is visible now, and I'm audible also.
Yes.
And
Yes,
as
sir.
Priya Madam has already informed, we will be talking about seismic hazard and estimation of earthquake forces. And a special focus will be on what changes are there in the code which is under revision. But before starting that, I want to talk for a minute on the topic of this webinar, wind and earthquake for tall buildings. So some of you may complain that why we are discriminating against gravity forces, because why we are taking only earthquake and wind, and earthquake and wind together. So we have to design any structure, including building, for all the forces which are coming on this, including gravity load, that is dead load and live load. But we all understand that any structure is inherently weak against lateral forces. Any structure is quite strong in the vertical direction. So let me tell you that as compared to the weight of the building, the earthquake force and wind force are much smaller. But still, these are governing the design. And during interaction with the field engineers, those who are designing, I discovered that wind forces are somewhat being overlooked. And I discovered that I myself do not understand that. And especially the dynamic effects of the wind, which are prominent in case of tall buildings, those are not properly understood. And then I thought that let's do these two lectures side by side, not one after the other, but together, so that we understand the similarities. I will show you that there are a lot of similarities between wind and earthquake, and at the same time there are some differences. So we will talk about those similarity and differences, and you can better correlate those when the two talks are together. So you listen to uh, Lakshmi Madam on wind, and now let us talk about earthquake. So when we talk about earthquake, what comes to our mind is some records like this. Now, if you compare these records with the record of the wind velocity, which you have seen just now in Lakshmi Madam's presentation, you can see that there is a similarity. These are very similar. These are also varying with time, and the frequency of variation is also similar, not very different. But there is a basic difference. And the difference is that in case of wind, there was a mean wind velocity. So these were fluctuating, the wind velocity was fluctuating about a mean value. Whereas in case of earthquake, it is changing about zero value. So it is changing the direction. Wind is not changing the direction, at least in the duration for which those plots were shown. It will take hours or days or more to change the direction. But in case of earthquake, the direction of the acceleration is changed in a fraction of a second. And we take advantage of that. Another difference with respect to wind is that in case of wind, we are taking a return period of 50 years, which Madam was talking, or in some cases, maybe more. But in case of earthquake, we are taking much larger return periods. We are talking about 2,500 years return period, which we are considering in our design. And now the revised code is talking about 5,000 year return period and even 10,000 years return period. So it is a much more rarer phenomena, earthquake. But the force caused during earthquake is much larger. Even when we say that wind may be governing design of a tall building in a particular zone, in a particular site, but still the earthquake forces are large. Why the wind is governing? Because in case of earthquake forces, we are using a response reduction factor. So we are designing for reduced forces. We are designing something like 10 to 20% or even less of that, what an elastic structure will experience. So earthquake forces are tremendous, but those are very rare. So that's why the design philosophy is slightly different. When we design for wind, we design our structures to remain elastic during the storm. But when we are designing for earthquake, we accept damage in our structure. And because we accept that damage, we can afford to design our structure for much lower earthquake forces. So that is the difference. Then the frequency content of both wind as well as earthquake is important. Unfortunately, both the frequency of content of earthquake as well as wind is overlapping with our tall buildings. Earthquake frequency are on higher side. Those are more towards low-rise buildings, whereas the wind frequencies are more towards tall building side. So tall buildings are having relatively lesser effect of earthquake and more effect of the wind from the frequency point of view also, because when you saw the energy spectrum which Madam has shown with respect to frequency, the micro and macro peaks. So there you can see that the micro peaks which are having a higher frequency, which that frequency is close to the frequency of vibration of our tall buildings. And that's why the dynamic effects become very important in case of wind also. So we have to take into account the dynamic characteristics of the buildings, both in case of wind as well as earthquake. And it was the dynamic effect of the wind, which most of the times I saw that people are missing. And that's why I thought that this equal importance giving to wind and earthquake is very important, and that's why we had this course of wind and earthquake together. So when we talk about quantification or measurement of uh, earthquake, how we can represent it? So basically, three parameters are important. If we look at the record, this record is quite random, and it's very difficult to make sense of this record. But when we look at the properties of this record, we see that the important parameters are amplitude of shaking, because force, earthquake causes an inertia force, and that inertia force depends on mass and acceleration. And larger the peak acceleration, larger will be the peak force. So peak force can be calculated using peak acceleration. And acceleration, velocity, and displacement, these are related. So peak amplitude, either in terms of acceleration or in terms of velocity or in terms of displacement, that is one measure of the damaging potential of the earthquake, or the amount of the force for which we need to design our structure. Second important parameter is frequency content. So as I said that uh, earthquake and wind both are random phenomena, so those have certain frequency band. The energy is located in a range of frequency, and if that range of frequency is close to the frequency of the structure, or the frequency of the structure lies within that band, the structure is going to experience larger forces. If the structure is beyond, outside that band, then it will be subjected to less forces. And then duration of, in case of earthquake, is also important. Duration in case of wind is not that important, but duration in case of earthquake is very important, because in case of earthquake, we are designing our structure to get damaged. In case of wind, also there can be a fatigue type of damage. So if the wind continues for very long duration, or there are some structures which are vibrating under wind, those can also be subjected to damage. But that will require very large number of cycles. So if those cycles goes into millions, then we can experience the damage due to repeated nature of stresses. But in case of earthquake, because we are designing it to get damaged, so that damage gets accumulated very fast. So within few cycles, dozens or hundreds of cycles, the structure will fail depending on its ductility. So the duration of earthquake is also very important in our design. Then how these parameters are governed by the natural phenomena. So three effects which we need to consider, and these have been underlined now in our revised IS 1893 part 1. So one is the source effect. So source effect depends upon the source mechanism, how the energy is being released, what type of slip is occurring at that source, whether it is a strike slip or a dip slip. Then how deep? Sometimes you might have heard this news that although the magnitude of earthquake was large, but because it was deeply buried in the earth crust, so the damage was less. So the depth will decide the characteristics, the three characteristics which we were talking, and also the distance from the source. So near fault effects will come if our site is very close to the source. So all these source characteristics we need to understand. Then path characteristics. So when the energy is traveling from the focus or hypocenter of the earthquake to the site, when it passes through the geomedium, then its characteristics get changed. And these characteristics are region specific. So like Lakshmi Madam was talking about, the wind characteristics in different continents are different. In the similar way, these path characteristics in different continents are also different. These depend upon the crust properties through which these earthquake waves are traveling. Then site effects, local site effects, generally related to the soil strata. So how the soil layers are there, what is the stiffness of those soil layers and depth of those soil layers, that also affects the earthquake characteristics, ground motion characteristics significantly. Now, similar to that spectral energy density, which we saw in case of wind, in case of earthquake, we are representing the amplitude and frequency characteristics together in terms of response spectrum. So this response spectrum, most of you might have heard it several times. So it is nothing but response of some single degree freedom systems. So why single degree freedom system? These single degree freedom systems are representing simplest type of structures where there is only 1 degree of freedom, which is vibrating only in one direction, and there is mass which can be lumped only at one point. So these simple structures, when these are subjected to an earthquake, and the peak response of each single degree freedom system is taken, and that is plotted with respect to period or frequency. Now compare this with the spectral density function which madam has shown in case of wind. So there were 2 peaks. Here we see a single peak, but sometimes if depending upon the local soil, we can have multiple peaks here also. So corresponding to the fundamental period and the higher mode periods of the soil layers, there can be multiple peaks also here corresponding to different frequencies or periods. But if we are talking about hard soil, there we will see that there will be a peak corresponding to short period or higher frequency. In case of wind, the peak is corresponding to much longer period, and that's why that becomes more critical in case of tall buildings. Whereas earthquake, if we see the spectral acceleration, it is more critical for the low-rise buildings, short buildings. So we can understand this effect like this, that if I put a rigid concrete block, so this rigid concrete blocks will try to move along with the ground. So whatever is the peak acceleration of the ground or peak ground acceleration which we discussed, almost same will be the acceleration of this block being very rigid. So this we call a zero period structure. Theoretically, zero period is not possible, but if its frequency is more than 33 hertz or period is 1 upon 33 second, then we can call it zero period. So this acceleration of this zero period structure is very important for us. This we consider as the representative of PGA. PGA, the peak ground acceleration, can be measured directly from the time history record also. But in place of that, all our codes are using this because this is a better representative of the energy contained by the earthquake. So this effective peak ground acceleration, we call it. So this effective peak ground acceleration or zero period acceleration or Z. So zone factor Z, which is given in our code, the current code as well as the revised code is also using this zone factor. So we have to understand what the zone factor is representing. So this zone factor is representing acceleration of a rigid concrete block if embedded into the soil, and its acceleration is measured, and we take the peak acceleration of this. That will give us the EPGA or the zone factor. Contrary to this, on the other extreme, we have a structure which is very flexible. You can think it like a balloon connected with a thread here, very, very flexible. So you can understand that this will not be affected by the ground motion at all. So acceleration will tend to zero, but the relative displacement you can see here will be the same as that of the ground. So its peak ground its displacement, relative displacement will be same as the peak ground displacement. So a flexible structure is representing the displacement, relative displacement of the structure, whereas a rigid structure is representing the effective peak ground acceleration. And real structure will be somewhere in between. So that we can obtain from this plot of the peak response of different single degree freedom systems. So our real structure is going to be somewhere in between. And If we are talking about a real structure, which will be multi-degree freedom system, several stories may be there. So it will not have one period. It will have several what we call natural modes of vibration. And usually the contribution of the first mode, which we call fundamental mode, is maximum. And for the higher modes, the period is less. The period shortens for higher modes. And the contribution of those also reduces. And total response of the structure comes from the contribution of different modes. So all the modes together, these define the behavior of a real structure. So real structure will have contribution from several ordinates of this response spectrum. The fundamental mode, which will be having the longest period, will have the maximum participation, and other modes, although their spectral acceleration may increase because those will be having shorter period, but their contribution usually will be small. In case of low-rise buildings, we can even ignore the contribution of higher modes, but in case of a tall building, we can't ignore the contribution of higher modes. It will be less than fundamental mode, but it is not negligible. We have to consider the contribution of higher modes also. For a real earthquake, we can plot this response spectrum either in terms of displacement. So that means that I take the peak displacement of each single degree freedom system and I plot that. I can plot the velocity, taking the peak velocity of each single degree freedom system, and acceleration. Most important to us, or conventionally the most used, is this acceleration response spectrum. And this acceleration response spectrum is important to us because we can get the force on the structure, on a simple structure, directly from here. We can read corresponding to the period of the structure, the spectral acceleration, and when we multiply that by mass or weight of the structure, we will get the seismic force acting on that structure. Conventionally, the horizontal components of earthquake had been considered in analysis because, as I said, that any structure is inherently weaker in lateral direction. In vertical direction, in axial direction, the structure is strong. So conventionally, horizontal direction or two components in the horizontal direction, those have been considered. But it has been observed that vertical component is not insignificant. Some cases in near field, it may be as strong as the horizontal component itself. So at least in some structures, the vertical component will be significant. So now we are having not only the horizontal component or horizontal response spectrum, we are also having the response spectrum in the vertical direction. And that shape also is given in IS 1893. We will talk about that. The most important value is this value here, the zero period acceleration, which I was talking, which is representative of peak ground acceleration, and we call it effective peak ground acceleration. So this is important. And in the code, what we see as the response spectrum, actually it is not response spectrum, it is spectral shape. And how that is obtained? That is obtained by dividing or normalizing the response spectrum by this value of EPG. I will come to that. Then the local site effects came into discussion after Mexico City earthquake in 1985. So after that earthquake, the local site effects were discussed a lot because a very unusual phenomena was observed in Mexico City. The earthquake occurred more than 300 kilometers far away from the city, but still it caused extensive damage. And the record is also very peculiar. So in this last earthquake, which you see, this last plot here, this is the Mexico City plot. And you can see that amplitude is very small. All these earthquakes are plotted to the same scale. So you can see that amplitude is very small. Still, this earthquake caused a lot of damage in the Mexico City. And the reason was that you can see here, it is taking much longer in reversing its direction. Or we can say that the frequency content or the predominant frequency of this earthquake was much lower. And unfortunately, that matched with the frequency of our structures in a range of height 5 to 20 stories. So those structures between 5 to 20 stories, those were severely damaged during this earthquake. Now, if you look at the response spectrum, so in Mexico City, the recording was done at two stations. One is this University of Mexico and UNAM, and then another SCT. So Mexico City is situated on the bed of a dried lake, and the thickness of the deposits goes on increasing from the bank. So near the bank, we have the foothills. So where rock outcrop is there, so UNAM is located on rock, but this SCT station is located on a soil bed of roughly 30-meter depth. And if we calculate the period of vibration of this 30-meter column of soil, this comes out to be about 2 seconds. And if we look at the response spectra plotted at UNAM and SCT, so we can see that the spectral acceleration near the SCT or near the 30-meter deep soil, it was much larger, 0.8 G roughly. Whereas at the UNAM, at the rock outcrop, that was much smaller, roughly 0.1 G. So 8 times amplification of the spectral acceleration was seen here. Or in other words, the force on the buildings having a period close to 2 seconds was roughly amplified by 8 times. And that was tremendous. Most of the buildings in that range could not sustain that, and there was large scale devastation in Mexico City. And this peak is also confirmed by a simple calculation. So this is the formula for calculating period of the soil site, 4H by Vs, where Vs is the shear wave velocity and H is the depth. So for 37.5 meter and the shear wave velocity, because this was deposited at the lake bed, so the shear wave velocity was loose soil, shear wave velocity was much less, and the corresponding period comes out to be 2 seconds. So the frequency content is also very important, and the local site effect or the type of the soil strata at the local site, that is affecting the ground motion significantly. And this needs to take it into account. Now, if we look at our current code, IS 1892-2016, it provides response spectrum like this, where this lowest one is corresponding to hard soil. So as I said, in case of flexible or not so stiff soils, the amplification will occur. So we can see that this amplification, this middle curve is for medium soil and the top one is for the soft soil. So as the softness of the soil is increasing, the spectral acceleration also increases. And if you remember from the code, the equation for this is 1.67 divided by T, whereas for the type 1 rock or hard soil, it is 1 over T. So roughly 67% increase in the spectral acceleration and the forces if our structure is located on soft soil at the same location. If the distance with respect to the source is same, but because of the difference in the local site soil type itself, there is 67% increase. What I want to highlight here is that actually this is not response spectrum. This is a misnomer. So it is not response spectrum, it is spectral shape. What is mean by spectral shape? That the response spectra have been normalized by EPGA. So when we normalize this by EPGA, we get this value as 1. So actually it is not response spectrum, but it is spectral shape. And this will be, or this can become response spectrum when we multiply it by ZPA or EPGA or effective peak ground acceleration or zone factor Z. So the same concept is continued in the revised code also, but there are some changes. So I want to highlight that. So if you look at the shape of this response spectrum, it increases linearly up to 0.1 second, then it is constant, and then it is 1 by T, 1 by 1.36 by t or 1.67 by t up to 4 seconds. So this range, here the acceleration, spectral acceleration is constant. We call acceleration control range. And from this corner point to 4 seconds, this is called velocity control range. I will explain why this is called velocity control range. And our current code is considering this response spectrum or spectral acceleration to be constant beyond 4 seconds. This is incorrect, and this has been corrected in the revised code. So in revised code, you can see, although the shape which you will see in the actual code which is coming will be slightly different. So this is from one intermediate revision. There it is more clearly explained, so I have taken that. So from 1 to 0.01 second, I said 1 by 33, so that comes out to be 0.03 second. It is constant, and it is equal to EPGA, effective peak ground acceleration. That's why the value is considered 1. Fortunately, we do not have any structure in this range which is having a period less than 0.01 second or even 0.03 second, because this will require a very, very rigid structure. Practically, we do not have structures here. Any period sometimes, if it is a low-rise building, a short building, some of the higher modes can go in this range. Because as I said, that higher modes have shorter and shorter period. So if we have to consider a very large number of modes, we are not getting 90% mass participation in large number of modes, then we have to, then some of the modes may come in this range. And if those modes come in this range, then spectral acceleration will be considered as constant. Then it is increasing up to 0.1 second. It is constant. This is acceleration control range. Velocity control range is now considered up to 6 seconds in the revised response spectrum. And beyond that, it is proportional to 1 upon t square. Earlier it was constant. Now it is 1 upon t square. So this is called displacement control range. As I told that in case of flexible structure, the displacement of the structure is governed by the displacement of the earthquake. So this range is representing the displacement or the ground displacement. It is not equal. It is some factor times ground displacement, because it will become equal to the ground displacement at very large, very long periods. In this period, it is some factor time displacement. Similarly, here in this range, the velocity, spectral velocity, is some factor times the ground velocity. Now, this is a plot of acceleration. How we can convert into velocity or displacement? Simply by multiplying it by, or sorry, dividing it by omega, we will get velocity and spectrum. And if we divide it by omega square, so omega square is nothing but 2 pi by t square, or we multiply it by, in other words, t square by 4 pi square, we will get the displacement spectrum. So if you do that, you will see that this range, in this range, we will get velocity as constant, and in this range, we will get displacement as constant. That's why we call, we define these three ranges as acceleration controlled or acceleration sensitive, then velocity controlled or velocity sensitive, and then displacement controlled or displacement sensitive. So now our code is, our response spectrum is very similar to what we have in EFC 7 or Eurocode. Earlier, the displacement, the acceleration was considered to be constant. That was wrong. It was not affecting the forces much, because in any case, acceleration here reduces significantly. And generally, the design will be governed by minimum force required by the code. So it was not affecting the force design, but it will affect the displacement a lot, because displacement is increasing here. So even it is proportional to 1 upon t square, spectral acceleration is much lower, the displacement will be peak, because it is to be multiplied by t square by 4 pi square to convert into the displacement, spectral displacement. And the period is long, t value is quite large. So that's why the displacement here is quite large. Then another issue which we have to keep in mind is that in case of an earthquake, we can record 3 components at any point. Then the orientation of these three components can also be any direction randomly. Any motion in space, 3D space, we can define by three vectors, three components. So if we measure those three components in any direction, we can uniquely define that motion. But when we are plotting the response spectrum, which I have discussed just now, we are considering one component, either horizontal in x direction, or horizontal in y direction, or vertical. So any of the three components we are considering individually in response spectrum. So the direction in which we are plotting the response spectrum, that becomes very important. So this plot here, this shows the peak value of spectral acceleration in each direction and variation of that spectral acceleration with time. So what does this show? That earthquake is not only changing in amplitude randomly, it is also changing in direction randomly. So sometimes the motion is oriented in one direction, in other time it is oriented in other direction. And if we are considering spectral acceleration in different directions, we will get a plot like this. So in this case, this is a far field. This plot is for a far field ground motion. And you can see that in this far field ground motion, more or less spectral acceleration in all the directions we are getting. Still, in one particular direction, it is peak. That peak direction we call ROT D100. ROT stands for rotation, and 100th percentile. That means the maximum value. And the minimum value we call ROT D0. So the minimum value, so if we see statistically, this is having the 0% confidence minimum value. It is having the 100% confidence or the peak value. So in other directions, it is somewhere in between. So when the codes are providing the response spectrum, they can have any of these conventions. So like ASC 7 is providing ROD D100, maximum response spectrum, which can occur at any site, considering all the possible orientations of our response spectrum. So this also becomes important. It's still not clear what our code is representing, and the revised code is also not mentioning this, but we have to keep this in mind, because in some earthquakes or at some sites which are close to the earthquake, we can have this Doppler effect. And what is this Doppler effect? The earthquake source, when the rupture takes place at the earthquake source, that is also occurs in finite time. It takes some time. Gradually, the rupture moves, and at each instant, it is generating a pulse. And those pulses can have a constructive or destructive interference. So when the constructive interference occurs, we get a pulse, velocity pulse. So suppose this is the record of the acceleration. We can get velocity by integrating this, and displacement by integrating like this. So you can see here, there is a velocity pulse here. So this velocity is occurring for significant time, and this pulse can be quite damaging. So in some cases, when we are near the fault, we can have this type of pulse. So near fault cases need to be considered with more care. And the revised code is talking about this effect separately. So near field effects, like in case of wind, you can have an analogy with those locations where we are experiencing cyclones. So there is an additional factor for cyclone prone areas. Similarly, those areas which are close to the sources, Himalayan area or anywhere where we are having our site close to the source, this phenomena is possible. And not only this, the directionality effect is also there. So this left one is a far field motion. So this motion from Chichi earthquake, it is recorded at a far field. And what you see here, that the spectral acceleration in all the directions are more or less similar. But for this particular earthquake, Morgan Hill earthquake, occurring at a site called Gallery Array number 6. So you can see the spectral acceleration in one direction is much larger as compared to the other direction. So this is something like polarization of light. So vibrations are occurring predominantly in one direction. So this type of effect is interesting and important to our structures, because if my weaker side of my structure is oriented along this direction, then the damage will be more. The other side, other direction of the structure, the other component on the structure will be having much lesser spectral acceleration and the force. So this directivity or directionality and pulse, these are two important effects which we need to consider if we are in the vicinity of the fault, if our site is located close to the fault. Then regarding estimation of peak ground acceleration or response spectrum at any site, two methodologies are available: the deterministic seismic hazard assessment and the probabilistic seismic hazard assessment. In deterministic seismic hazard assessment, as the name suggests, we get a single value of the hazard, whereas in probabilistic hazard assessment, we get different values associated with different probabilities of occurrence. So depending on what probability of occurrence or return period we want, accordingly the value is going to change. So the steps in case of deterministic seismic hazard assessment, quickly I can explain. So we consider all the faults in the vicinity of our site, and when I say vicinity of the site, it is 300 kilometers. So at least those sources which are within 300 kilometers of the site, all those sources we have to consider. Those sources may be defined either as line or an area, so or a surface which is dipping. So these source characteristics are to be known. And when we talk about source characteristics, first of all, the magnitude, what magnitude earthquake this source can generate, what magnitude earthquake this source can generate. And then we consider the distance of the site from the source, and depending on the distance, we consider attenuation of the energy which will be released here. Because we know if energy is released at any point, as we go away from that point, the energy will be distributed in larger volume. And when the energy is traveling in the form of elastic waves through the soil or rock medium, it is subjected to some damping, some energy dissipation takes place. So depending on this distance, estimation of the distance, generally we take the closest distance or any other appropriate distance. So based on that, we can calculate the intensity or PGA or response spectrum due to each source at this site. And then we take whichever source is giving us the maximum value of PGA or response spectrum or spectral acceleration at a particular period. That source we call governing source or governing earthquake, and we draw the response spectrum for that earthquake. And that we use in our design. These are the steps in deterministic seismic hazard assessment. Now, getting the magnitude of earthquake associated with a source is the most difficult and uncertain part. So we depend, because records of earthquakes for such long durations are not available, which are required. We are talking about the return periods like 2,500 years, 5,000 years, 10,000 years. So those return periods are very, very large, very, very long. And recording for such, or even the historical evidence of such rare earthquakes are not available. So what is done? We take use of some statistical regression methods, and this Welsh and Copernicus, they have given this relationship. So based on these relationships, we can calculate the magnitude, which is, or the potential of that source, what magnitude earthquake it can generate in future. Now, interestingly, in our revised quote under revision for the Indian continent, Indian subcontinent, different sources, 33 different sources have been identified. So different zones, these zones are considered as one source, and for each source, the magnitude is also defined. So for these 33 sources, the magnitude are also defined for probabilistic as well as deterministic. What magnitude we have to consider in probabilistic and what magnitude we have to consider in deterministic. So probabilistic, of course, it comes with the probability of occurrence. So 8 magnitude earthquake, but a lower probability of occurrence. 6.5 magnitude earthquake is assigned in deterministic seismic hazard assessment because it is a deterministic value. And some attenuation relationships are also provided. So when we do the probabilistic seismic hazard assessment, we consider the variability or uncertainty in each of these parameters. So we consider the variability in the magnitude, we consider the variability in the distance, and we also consider the variability in the equations which we are using to calculate response spectrum at any site using the magnitude and distance from the source. So if we consider the variability of all these input parameters, we will get a value of the response spectrum or acceleration. Using this probability theorem, we will get that, and there will be a distribution, or in other words, there will be different values corresponding to different return periods. The conventionally considered return periods in the design codes, especially if we talk about ESC 7, ESC 41, and ASTO code. So these return periods have been conventionally used. And most commonly referred to earthquakes are this 50% probability in 50 years. So 50 years is the design life of our normal structures, which we discussed in case of wind also. So 50% means this is something like occurring once, at least once during the lifespan of the structure. We also call it serviceability earthquake because if this structure has to occur, this earthquake has to occur during the lifetime of our structure, the structure should remain serviceable for that. And return period is approximately 7 to 2 years. And then another one, this is very important because world over people are considering this level of earthquake for design. 10% probability in 50 years, return period of 475 years, and we call it design basis earthquake. And 2% in 50 years, this is the earthquake which we are targeting for safety of our structure. So we presume that this is quite rare earthquake, and if our structure can survive this earthquake without collapse, then the purpose is served. If the structure is even damaged fully, but it has not collapsed, we will construct it again. So this is what we're targeting, a return period of 500 years roughly, 2475 years more precisely, roughly 2500 years we say, and this we call maximum considered earthquake. So it is interesting, we are targeting this earthquake, but we are designing for this 475. So we are designing for 475 years, and whenever we are designing, there is some hidden strength. So that hidden strength comes because whether we are using working stress method or limit state method, we are using some factors of safety, partial factors of safety, and also we are using characteristic strength in place of average strength. So when we are using working stress method, the hidden strength is much larger. So along with working stress method, we use serviceability earthquake. So if I have to use working stress method in design, the earthquake I should use for design is serviceability level earthquake. Because there is a ratio of the hidden strength between working stress method and limit state method, that is 1.5. So the design strength of the same section or same structure, if I estimate using limit state method and I compare it with what I have estimated using working stress method, there will be a ratio of roughly 1.5. And actually, the ratio between serviceability level earthquake and design basis earthquake is also 1.5. On the other hand, even if I'm designing it using limit state method, still there is some hidden strength. And that hidden strength varies 1.5 to 2, between 1.5 to 2. And the ratio of MC level earthquake coordinate, and DV level earthquake coordinate is also roughly 1.5 to 2. So this hidden strength take care of the MC level earthquake. So although we design for DV, but our target is MC. This we have to keep in mind. In case of bridges, ASTO uses a return period of 1000 years, 975 years to be more precise, and this corresponds to 7% probability in 50 years, or if we convert into 50 years return period, then that will correspond to 5% in 50 years. 7.5% in 75 years will be roughly 5% in 50 years, so it is close to it. So the bridges being costlier and being designed for larger lifespan, those are designed for 975 return period earthquake, whereas the buildings are designed for 475 years return period earthquake. And actually, we are targeting this MC level. So I will skip this. So in our current code, if I have to calculate or I want to obtain the response spectrum corresponding to DV or MC, how can I obtain it? So I told you that what is given in the code is a spectral shape, and this spectral shape is normalized by EPJ. So it is wrong to say that this is SA by G. Actually, it is SA by Z, because it is divided, the response spectrum is divided by the Z value. That's why this becomes 1. So actually, it is SA by Z, normalized spectral shape, and when we multiply it by 1.5 Z, which is given in the code, because the Z given in our code is corresponding to serviceability level earthquake. Rather, Z by 2 correspond to serviceability level earthquake. It is the median value obtained from deterministic seismic hazard assessment. And in deterministic seismic hazard assessment, actually there is no concept of DV or MC, because that gives just one value. Either we can take mean value, or we can take mean plus some factor times sigma. So mean plus 1 sigma is generally considered as MC, equivalent to MC, which we are obtaining from probabilistic seismic hazard assessment. So for equivalence, we can multiply it by 1.5 Z, then it will become equivalent to MC. If I multiply it by 0.75 Z, half of this, then that will correspond to DV. And if I multiply it by Z by 2, or 0.5 times Z, then this corresponds to serviceability level. So if you have to interpret the current code in terms of DV, MC, you can interpret it like this. But soon, within few months, it is going to be changed. And this factor of 1.5, you can ask from where that 1.5 is coming. So if we compare our load combinations, because 1.5, this factor in our code is given in as load factor. So only our code currently is giving load factor greater than 1, whereas other codes, Eurocode as well as ASC 7, here I'm showing ASC 7, this is giving a load factor of 1 for earthquake. So EV is the vertical component of the earthquake, EH is the horizontal component of the earthquake, and load factor for both is 1. Whereas the load combinations corresponding to working stress method, which should correspond to serviceability level earthquake, the load factor is 0.7, and you can see that ratio of these is 1.15. Our code, current code, has reverse approach of this. It is having a load factor of 1 for working stress method, because the earthquake force which is calculated corresponds to serviceability level earthquake, and then it is multiplied by 1.5 to get the limit state method, or what we call LRFT design. So there it is being multiplied by 1.5, so it is just reverse of that. Now the revised code has hazard or estimation of earthquake forces using the probabilistic seismic hazard assessment. So current code was based on deterministic seismic hazard assessment. The revised code, which is going to come soon, I hope in few months, that should be out. So that is based on probabilistic seismic hazard assessment. And the concept is that different structures will be designed for different return periods. So it is the same concept as we have used earlier in terms of importance factor. So when we were applying importance factor, let us say for important bridge or building, we were applying an importance factor of 1.5. So what does that mean? Normal structures we are designing for DBE corresponding to 475 years return period. If I multiply it by 1.5, then it is approximately equal to 2475 years. So in other words, I was designing that for an earthquake with longer return period. So the revised code is defining different return periods for different structures. And what we see here is different types of structures, different parts are there. So now there are 12 parts proposed. Some of these parts have been completed, some of these parts in revision, and some of these parts will come in future, like tunnels and coastal structures. This may come in future. But dams, pipelines, base isolated buildings, industrial structures, those are more or less prepared. So those are going to come very soon. And the major changes which the code has proposed is the 12 parts. Out of that, part 1 is now dealing with general provisions. Earlier, part 1 was general provisions and buildings. So it is not buildings have been removed from that. Those have been taken to a separate part. Part 1 is general, which is giving the hazard, which is applicable to all types of structures, because it is giving just the hazard with respect to return period. Then a revised earthquake zoning map. The zoning has been changed. I will show you just now. And the response spectrum, as I have shown, has been now provided up to 10 seconds. Earlier, it was only up to 6 seconds, and 4 to 6 seconds was taken constant. Now, not only the shape has been changed, but the shape has been plotted up to 10 seconds, because some of our tall buildings were having period close to it. And our designers were having difficulty in taking the value of spectral acceleration for those long periods, because the response spectrum was not defined. So now the response spectrum is defined up to 10 seconds. And horizontal coefficients are provided for different return periods. Then now the code also talks about how to select ground motions. So for time history analysis, we need selection of ground motions. So code is talking about selection of ground motions also. And to consider the soil flexibility, also a method is given. Similarly, the liquefaction potential procedure, which was given earlier, has been slightly modified. And protection of architectural elements, non-structural components. Earlier, our code was not dealing. So this code, IS 1893 Part 1, this is also talking about calculation of forces in case of non-structural components. And interestingly, the load combinations have been changed. Now these are very similar to what we saw in case of ASC 7. The load factor is 1 for earthquake, whether it is limit state of serviceability or limit state of strength. Limit state of serviceability combinations are also to be used for working stress method. So the load factor is 1, but the earthquake load calculated in case of limit state of method and working stress method or serviceability earthquake, the return periods are different. And those return periods I will show just now. So the code now, the revised code divides the country into 5 zones now. Earlier there were 4 zones, zone 2 to zone 4. Now there are zone 2 to zone 6. And this northern Himalayan part and the Gujarat region, this is shown in zone 6. So this new zone has been created, and this is the most seismic zone, because most of the major faults are in this region. And zone 4 has been divided into now 3 zones. Part of it is in zone 4, Delhi. Then this portion here between foothills and Delhi, this is in zone 5, and Himalayan region is in zone 6, which was partly in zone 4 and partly in zone 5 earlier. And the structures have been divided into different categories and corresponding return periods, which are to be used in strength design. So in case of limit state method or strength design, spatial structures, And those special structures, which are very important structures, those will be designed for a different period of 5,000 years, 4975 years. So more than MCE, roughly 1.5 times MCE, these structures will be designed. So which were earlier were being designed for DBE multiplied by okay, those were being designed for DBE multiplied by importance factor. So importance factors, if we take at as 1.5, so roughly those were being designed for MC. Now these will be designed for 1.5 times of that force. Then critical structures, these will be designed for 2475 years. We can think it similar to our important structure in the current design. Then important structures, these will be designed for 975 years. We can think something like an importance factor of 1.2, and normal structures, of course, 475 years, DBE, importance factor equal to 1. Similarly, in case of working stress method, special structures in working stress, which were earlier being designed for serviceability level earthquake, 75 years earthquake, with an importance factor of 1.5. So that becomes something like DBE 475. So those will be designed for 975. So a new class has been created here of special structures, and these special structures will be designed for 1.5 times the forces for which we were designing our important structures earlier. Then these critical structures are similar, critical and important structures are similar to our 1.5 and 1.2 load factor structures, and normal structures, of course, as usual, will be designed for serviceability. Now, the code also provides, because different return periods are used, so Z factor for different return periods. So just now we discussed this 2475 years MC level earthquake. This is important, and this is to be compared with 1.5 times Z in the existing code, because earlier code, that 1.5 factor, or the current code, I should not say earlier, it is still there. So the current code, there is a load factor of 1.5. So if I take the highest zone 5 in the current code, that is 0.36 into 1.5, so 0.54. So in place of 0.54, now the value of zone factor is 0.75. So in zone 6, there is roughly an increase in the hazard of 1.5 times in zone 6. Whereas in case of zone 2, earlier the factor was 0.1, so here there is no increase. It is 0.15. And in zone 5, we can we can compare it with earlier zone 4. So here also we can see that there is an increase. And the ratio between 475 and 2475 year earthquake, if you see, the ratio is varying between 1.5. So here it is exactly 1.5, 0.5 to 0.75 to 2. Here 0.075 to 0.15. So the ratio is higher. The ratio between DBE and MC level earthquakes is higher in lower zones, and it is smaller in case of higher zones. So this ratio also varies within the country. It is not same. Similarly, this 4975 years earthquake is also required. So this is also provided. And you can see that ratio is roughly 1.2, 1.3 to 1.5. In that range, it is there. So some of the structures now will be required to be designed for this. It will cause an increase in the earthquake. For if we assume the zone factor to be same as the current code, then there will be an increase because of this increase of 1.5, roughly 1.2, because of the change in the design return period, and also because of the change in the hazard. So Himalayan important structures like Himalayan bridges, those will be designed for roughly 2 times the force for which those are being designed currently. Now, for site classification, there is a better classification now based on SC7. So similar to SC7, different classes are defined depending on shear wave velocity. In Eurocode also, there is a classification. There is slight difference between Eurocode and ASC 7. So what is there in American code, the same has been adopted in our code. So site class A, B, C, D, E, based on the shear wave velocity. So if the shear wave velocity is greater than 1500 meter per second, then it is hard rock. So A is hard rock, B is medium or normal rock, we can say. So actually the reference class is this B. So A and B, these both are rock, and these have been put together in the code while defining the responsive spectrum. It is considered to be the same. Then C is soft, not soft, medium soil between 360 to 760 meter per second. D is soft soil, and E is very soft soil, where the shear wave velocity is less than 180. And these response spectra are defined for A and B. It is same as I said just now. Then C, something like medium soil, and D is something like soft soil. For E class, which is very soft, the response spectra is not defined in the response spectrum is not defined in the code. We have to go for site specific analysis for that. And this depends upon the average shear wave velocity. So how to calculate average shear wave velocity, and how to get shear wave velocity from n value, the SPT values, that is also now defined in the code. So if I have the shear wave velocity measured directly, or I have the n value, I can get the average shear wave velocity, and the classification can be done. Then if you look at ASC 7, it provides two amplification factors for response spectrum in acceleration controlled range and velocity control range. So in velocity control range, you can see that for D, this factor is something like 2.4 to 2 in this range we are having. Currently, our code is having this factor as 1.67, which is on lower side, and our revised code has changed that to, if we consider for site class D, this factor is now 2. So in place of 1.67, we are having 2 by T. So this amplification factor due to soil has been increased to 2. This 12, which is in the displacement control range, this can be obtained by the same factor. So actually the amplification factor is 2. But this is not there in acceleration control range. If we look at the AC7 values, we are having a factor FA also, which is in acceleration control range. So in acceleration control range also, the response spectrum is to be amplified by 1.6 to 1.4 times. So that factor is not there. And this factor we can see, if we are taking 2, it is nearby. It is what is here, it is close to, but still it is on lower side. In case of low seismic zones having very soft soil, this factor can be up to 2.4, whereas our code is giving 2, so it is still on lower side. So then the code also defines the value of spectral acceleration below the ground level. So at 30 meter, it will become 50% of what we have at the surface, and in between it will be reducing linear. Then vertical ground motion. So in vertical ground motion, the shape of the response spectrum is to be multiplied, whatever we have in the horizontal direction, that is to be multiplied by this factor delta V. And this delta V itself is a function of period. So this also depends on the period. So in the period range between 0.01 to 0.1 second, it will be multiplied by a factor of 0.8. But beyond 0.1 second, it will be multiplied by 0.67, 2 by 3, which we are having currently also. So very few structures or only higher modes of our multi-degree freedom systems will come in this range. So we can see that in the short period range, the spectral amplification in vertical direction is higher. In the longer period range, beyond 0.1 second, it is 2/3. So in very short period range, less than 0.1 second, the vertical response spectrum is more than 2/3. It is 80% of what we are having in the horizontal direction. Whereas in periods greater than 0.1 second, it is same as we are having currently, 0.67 times the horizontal response spectrum. Then the code also provides modification factors for damping. So different structures, if we have to modify for damping, then these factors are also there. So currently we are designing for 5%. All our structures or the reference response spectrum, which is given in the code, corresponds to 5% damping. So more than 5% damping, this formula can be used. Between 0.5% and 5%, this formula can be used. So the damping formula, which is varying in different damping ranges, that is also provided in the revised code. Now, coming to the calculation of seismic forces and displacement, the expression remains same. Only thing is that that 2 here, which we were having earlier, that is missing. Now we are not using Z by 2, we are using Z. So earlier, when we were using Z by 2 and then multiplying it by 1.5, actually we are calculating these forces for DB, design basis earthquake. But now we have to take the value of Z for the corresponding period. For normal structures, the Z will be corresponding to DB. For important structures, critical structures, this is going to be more than DB. So that value is to be taken, and this ANH TH, this is nothing but the shape of the response spectrum, SA by G in our current. Rest of the procedure is same, and similarly in the vertical direction also it can be calculated using the same formula, but you note down here in vertical direction there is no response spectrum, no response reduction factor. So spectral shape is there. This A and V is the shape of the response spectrum, and this is nothing but delta V times A and H. So whatever is the shape in the horizontal direction, we have to multiply that by delta V, and no response reduction factor, or in other words, response reduction factor equal to 1, because in vertical direction, energy dissipation cannot take place. So this is going to increase the vertical component significantly because this R value is not. So like earlier, we were designing horizontal cantilevers for 5 times the vertical force we were getting, and that force we were getting using response reduction factor. So in other words, we were nullifying the effect of the response reduction factor. Same thing is happening here. So for all components for the structure, we will now taking this 5 times force. Minimum design force, although I saw it in one earlier version, which was put in wide circulation, but the last revision which I have seen, there is no, I could not find this. Maybe this will come in when the final draft of part 5. Now ISA 93 part 5 will be related to buildings. So when that part is finalized, I expect it to be there. So a minimum force will be specified, because we have seen that in long period, especially long period structures, the value of SAYG goes on reducing. So even if the period of the structure is very long, we have to design that for a minimum earthquake force, and that minimum earthquake force will be specified. In IS 16700 for tall buildings, that minimum force, minimum seismic coefficient is already defined, that for what percentage of the weight we have to consider. Then design displacements. In one of the revisions, you might have seen that this lateral drift permitted by the code was depending on the zone. So in zone 6, it was something like 0.002. So now that has been changed. This interstory drift is constant, same as in our current code, 0.4% interstory drift in all the zones, maximum interstory drift. And this is going to govern the stiffness or the size of our shear walls and members in case of tall buildings. Then the last part I discussed that the code has also, the revised code is also providing the design criteria for non-structural components. So it is well known now that similar to the amplification we have seen in the soil, the ground motion gets amplified within the building also. So if I measure the floor acceleration at near the top of the building and I compare it with the base, then near the top I will get roughly twice, 2 times to 3 times of what I am getting at the base. That will also depend upon the intensity of the shaking. So when we are having higher intensity like MC, then the structure will get damaged and it will dissipate energy. In that case, that amplification will reduce. But in case of lower intensity, more frequent earthquakes, let's say submersibility earthquake, the structure will remain elastic. And when it is elastic, the amplification is more, maybe in sometimes more than 2. But because we are designing for a higher return period, so that's why this factor is considered to be 2. So 1 plus x by h, where x is the label at which we are considering our non-structural component, and h is the total height of the building. So at the top, x will become equal to h, so this factor will become 2. So JAD is that corresponding to the return period, which is defined in that table depending upon the importance of the structure. Then this is the importance of that architectural or non-structural components. So it has its own importance factor. And then this is spectral amplification factor. So like we have the response spectrum at the ground, we can have a response spectrum at the floor also. And whatever is the peak floor acceleration, similar to PGA, we have a PFA, peak floor acceleration. The spectral acceleration can be higher, or rather it is much higher. So depending on the period of the structure, this is to be estimated. And again, R, response reduction factor for the non-structural component, it will depend upon the ductility or the amount of inelasticity which we are going to permit in the non-structural component, multiplied by the weight. So it is similar to what we are doing in case of structural components. Only thing is that here this amplification factor is coming, 1 plus x by h. So at base it will be equal to 1, and at roof it will be equal to 2, and in between it will be increasing linearly. And minimum 4% of the weight of this non-structural components we have to design for in the horizontal direction. And code provides the value of this amplification factor and response reduction factor. And you can see that the maximum value of amplification factor is 2.5. So this 2.5 is same as we are having in case of ground response spectrum. So in case of ground response spectrum, the peak value is 2.5 of the EPGA, effective peak ground acceleration. So same value we see here. This is representing the period of that component which we are considering, non-structural component. And the response reduction factor, again, the peak value is 2.5. So in some cases, both response reduction factor and this amplification factor will cancel out each other. And in some types of non-structural components where large deformability is there, which can deform large, this response reduction factor can go even up to 3.5. So the last thing which the code is talking about, I will just take 5 more minutes and try to finish this, is time history analysis. Now the code is talking about time history analysis and how to select the time history analysis. It will also provide in which zone for which type of structures the time history analysis or response history analysis may be required. So in those structures where we are not able to excite 90% mass, the irregular structure or very tall buildings, it may be, or buildings with basement, it may be possible that we are not able to excite 90% mass. So those structures need to be designed using time history analysis. Rest of the structures, response spectrum method using mode superposition is as good as the time history method. and that is acceptable as a dynamic analysis if mass participation we are able to get up to 90%. So in case of time history analysis, if we are performing linear time history analysis, minimum 3 sets, and if we are using non-linear time history analysis, minimum 11 sets of recorded ground motions are required. So these time histories, these have to represent the design response spectrum. So there are two sources of these. Either we can take recorded time histories and modify those recorded time histories in such a way that those are representing our target response spectrum, or we can simulate or artificial accelegrams we can generate. Artificial accelegrams are not preferable because these are distorting the natural characteristics of the ground motion. Recorded accelegrams, recorded time histories of ground motions, those are desirable. Now, two types of scaling is possible. One is amplitude scaling, where we multiply the whole time history by a constant factor. So what should be that factor? One way is that we scale it in such a way that the PGA is matching it. So what you see here, this was the original, this is the original response spectrum. This is the target response spectrum. I have multiplied by this factor so that EPGA of the ground motion becomes same as the targeted EPGA. So it can match the EPGA or the zone factor. But that necessarily does not mean that my response spectrum will also be matched. At other periods, especially at the period of interest, where my building period lies, this may be very different. So it is not multiplying by PGA or scaling by PGA is not a very desirable method. What we do is we take the period of interest and then multiply it by this period of interest or scale it at this period of interest, so that at this period of interest it is matching with my target response spectrum. But again, I can match at one period only. At other periods, it may be different. It may be either close to my target response spectrum or it may be very different from my target response spectrum. So what we have to do, we have to consider a number of such time histories scaled with or scaled at the period of interest in such a way that the mean or median of those time histories is very close to the target response spectrum. Alternatively, there can be spectral matching. So I can take a recorded time history and I can modify its frequency constraint in such a way that it is matching with my targeted response spectrum, and there are software available which do that. But we have to understand this is unnatural. A natural earthquake will not have this type of response spectrum, because the response spectrum which we have obtained as result of PSHA, probabilistic seismic hazard assessment, and given in our code, it is sort of an envelope. So it is representing an envelope of several earthquakes. So no single earthquake can have a shape of this response spectrum. And if artificially we are fitting this, then we are making our ground motion conservative. So this is acceptable, but it is on conservative side in case of linear time history. In non-linear time history analysis, this is not allowed, and we have to use selected ground motions, recorded ground motions, scaled either with respect to the spectral acceleration and consider minimum 11 time histories, so that the median of those 11 time histories is close to this response spectrum. So there are some sites where we can download our ground motions, what we call a strong motion database. Some of these have been quoted in our revised or under revision code also, and you will find that reference. Then there are some software which help you in processing those time histories. For example, the Seismomatch. Seismomatch you can use to make the time history compatible with your target dispatch. So in frequency domain, it will change, and it is using a wavelet transformation method. Wavelet transformation method is trying to preserve to the extent possible the natural characteristics. As compared to artificial earthquake, this is much better, but still it is also not natural earthquake. Then another software, Quake Manager, is available, which helps in selecting the ground motions and scaling those. Some public domain free softwares are also available based on the wavelet Seismosoft procedure only. This software is quite useful. Only thing is that you have to use it in command mode. GUI is not there, but it is very useful software. Thank you. That's what I wanted to discuss. I will now unshare and we can take up the question.
Yeah. Thank you, Dr. Yogendra Singh, sir. As usual, you have given a wonderful view of the new code. We have been already done it also in past. This was very important from practical engineers' point of view because there are going to be a lot of changes and especially time history, and participants will be eager to know when it will be out. Any idea?
There was a meeting day before yesterday, and in that meeting, the chairman informed that no more changes because the revision was also getting changed. A lot of input was coming from different sources, and they were changing. So, in response to some discussion on dams, he has informed that no more changes. It will go to printing now.
And then part
So
1
we
and
hope-
part 5 will be coming simultaneously or otherwise? Because
I think so. I think so. Part
yeah,
1 and
because
part 5
otherwise
may
it will
come
create a
simultaneously.
huge confusion.
No, part 1, part 5, and also 13920, part 1 and part 5. These will come together.
Yeah. I will take questions now. Before taking questions, I'll just some information to the practical engineers. This is very important from the point of view of also PEB structures. Now in India especially, most of the PEB people are using American codes for whatever reasons. That reason is known to everybody, but they have to have economy. And what they do is they take the basic forces from basic wind and earthquake, basic forces from the Indian codes and then use load combinations from American codes, which is not correct, which we have to always resist as a consulting structural engineers. But this is the reason because the basic things are different and then they result in an economical structure. But that is absolutely not correct, and hopefully that will change now. That's so.
Yeah, that once that load factor has been now corrected to 1,
Yeah,
and it has been included in the JED. So now that advantage or economy they were having, that will.
but as it is, it was not correct because they
that was not
use,
correct.
they
That's
cannot
why
use
I'm
load
putting it
factors
in
like that.
inverted.
Yeah. As it is, it was not correct, but it was going unnoticed because by the softwares, when you say American codes, they take the load combinations that way. So you have to change the load combinations. We do insist on that many times, but many times they are going like that only. And we'll take the questions. While considering the response spectrum, is it necessary to check the serviceability check of static earthquake? In response spectrum, we check drift and deflection without scaling. Please clarify.
Although I could not understand this question
I
fully,
also didn't
but
understand.
it is arising because of a confusion which is there in our current code, where it says that while calculating the drift, we need not to take factored. But that was not correct. Actually, this interstory drift of 0.4, this is at the factored earthquake. Now that issue will not be there because that load factor has been done.
Next question is, sir, why SA by G value is less in between 0 to 0.1 second in the response spectrum?
between 0 to 0.1 second.
So 0 to 0.1
Yes,
second.
it is increasing linearly.
Yeah.
So
0 pin.
yeah, that is based on the frequency content.
Hmm.
So the frequency content of earthquake, based on the frequency content of the earthquake, when response spectrum is plotted. So for very rigid structures, also the acceleration is small, and very long period structures also the acceleration is small. And in between the 0.1 to 0.4 second, I hope I'm audible. My voice is clear or there is some issue?
No, your voice is clear. There is a
Okay.
rain voice here. No issue.
Okay. That's why you were shielding your ear. So I was just thinking that whether I'm not audible.
No.
So that depends upon the frequency content of the earthquake. In case of wind, the frequency content corresponding to much longer period is there. In case of earthquake, the peak frequency content is between 0 to 10 hertz. So 10 hertz corresponds to 0.1 second. And there can be frequencies up to 33 hertz also. But the energy there is much less. That's why the spectral acceleration corresponding to those reduces. It is something similar to that spectral range, which in case of wind, which Madam Lakshmi was explaining between the macro and the micro peaks. So there is a frequency range in which energy is not much in the wind. So something similar.
Thank you, sir. Next question is, I have a question on a type of soil to be used. I have a building which has pile foundations, end bearing, and partly friction piles. First 5 meters has clay and rest is hard rock. Pile is embedded in the rock. For analysis, what type of soil to be considered in this case?
Okay. So now I have not shown that here, but the revised code is providing the depth up to which we have to consider the shear wave velocity. So it is not only in top 30 meters, it is providing us the depth, and the depth below the pile foundation will also come into picture. And an average shear wave velocity is to be calculated, and that average shear wave velocity is to be used. And that depth, how much should be that depth in case of a shallow foundation, raft foundation, pile foundation, those details are now given in that. So this situation will be covered by that clause.
Thank you, sir. Next is how frequency content are included in any design criteria. Is it through only response spectrum? Can you please explain a little more?
Yes, it is through response spectrum only.
Yeah.
So response spectrum of any ground motion is including two parameters of the ground motion: amplitude, that means PGA, and the frequency content. It does not include duration. Duration effect cannot be considered using response spectrum. For that, if I have to model that effect of duration also, then I need to do nonlinear time history analysis. But frequency content and amplitude are taken care of by response spectrum.
Thank you, sir. Is new code provides criteria for guide mast and suspension bridges? That must be separate.
Suspension bridges, I don't think it is yet covering. There is a part of IS 1893 being developed for bridges also, but that is yet to be completed. It's still the process has just initiated.
Thank you. Next is, what is the damping factor to be used for composite construction, like steel tube columns filled with concrete?
I don't think the code is going to cover. So when there will be a code on composite construction, that will perhaps explain that. But in absence of that, till that is not there, take a conservative value. But our current code is giving the same value for steel and concrete. So there is no confusion. Same value will be applicable to composite because it is not changing. But suppose it was different for steel and different for concrete, then this question would have been a problem.
Thank you. One practical questions: in how many modes 90% participation should be achieved to avoid time history analysis? Are there any guidelines? People are scared.
No, there is no guideline. So in some cases, for example, if you are analyzing a building with basement, you may need 200 modes.
Yeah.
If you are designing a cable stayed bridge,
Hmm.
then also you may need 250 watts.
His question is to avoid time history analysis.
Yeah, if you are able to achieve even 200 or 300 or 500 modes,
Okay.
if you are able to achieve 90% mass participation and you are considering all those modes,
Hmm.
then time history analysis is not
Not
required.
required.
Many times it also depends on
Yeah.
which whether you're using eigenvalue or Ritz analysis method. So
Yes,
the
that's another important
Mhm.
input, that in place of eigen modes, you can also perform Ritz factor. So if you are able to find 90% participation using Ritz approach, Ritz factor, you can use that as well.
Next, also a practical question in shear wall bearing structures, that is my1 walls we are talking about. Shall we consider time history or we can design by response factor?
I mean, the question is much before that, what response reduction factor value we should use.
Yeah, so that's correct.
Because that is not known, because so far our code does not cater to my1 types of structures where we are having continuous
Correct.
shear
That
walls.
is not covered
It's
even in new
related
code.
with slender shear walls,
Yeah.
where height to length ratio is more than 2. So in case of my1 walls, the height to depth ratio will be much smaller. So it doesn't cater to that type of. So we do not know what response reduction factor.
And that is
And
neither covered in
I do
new
not
code.
know how our designers are designing.
Yeah.
Somehow they are designing.
Correct. Some laws, philosophical, so many major changes done in new code. So was design as per 2016 code is not appropriate, and should we redesign those buildings as per new code?
That depends on the owner. If you want to be safe as per the new code, you have to redesign. You have to do retrofit. So code doesn't talk about this, that whether what you should do with your existing structures. But some of the structures in some zones will definitely become unsafe as per the new code, and it is an open question: what should we do with those structures?
I have one small question, Arvind, to ask,
Yeah.
if you permit. Yeah. See, it's a practical scenario. We are designing the building for earthquake and wind. The same structure is designed for both the different load cases. Earthquake force being having a parabolic distribution, the lower floors get affected more. Whereas for the wind, uh, the forces are, or the stresses are very much on higher side, even on the middle zone of the building or the top zone of the building sometimes. So a particular case or a scenario we meet when, the earthquake forces or the wind forces, earthquake force reduce such an extent, that the wind force are more than R times the earthquake force, so 4 or 5 times the earthquake force. So this structure becomes elastic when we design for the wind. It remains in elastic zone on upper floors, and the ductility really doesn't matter. But however, we'll have to design for we have to follow all the ductile clauses. But can we get some relaxation in using some of the ductile clauses like capacity design and all?
So that question, in fact, was pointed out in day before yesterday meeting. And question was that if we are designing our structure for earthquake with R is equal to 1, do we still need to do ductile detailing? So answer was yes. Why? Because earthquakes larger than what we are designing for can also occur. So when we are doing ductile detailing, the structure has the margin to absorb.
That's
But it
right.
is a debatable point. Code doesn't say anything clearly. Some of the designers, they are, especially in bridges, there are many situations where structure remains elastic, like you have seen due to wind, then it is because of the serviceability checks. So if the structure remains elastic, whether we should do ductile detailing or we should not, it is debatable.
Right.
So if you are thinking up to MCE only or the design level earthquake only, then you can say that there is no need. But we have to keep in mind that earthquakes larger than that also can occur. And earthquake resistant design is like a premium. You are paying for an insurance. More premium you will pay, more
More
cover you will
benefits you
get.
get.
More
Right.
cover you will get. So you have to also see a balance between the economics and. But many buildings now, the rates of the real estate are so high that structural cost is nothing. So there, if you do ductile detailing, actually cost-wise it is not an issue.
Sir, but that's still the efficiency of design is measured by the kg per square feet ratio, So
The trend is changing. Not all the builders are doing like that.
right.
A new trend has come. At least two builders now I know who are designing in Zone 4 for Zone 5.
Yeah.
And they say designer is hesitant to apply those checks, but the builder is saying, no, we have to follow the revised code.
Okay. Yeah, thank you. We continue with the questions. Why different angle of excitation with reference to building orientation are not considered in seismic analysis? They are considered.
So actually, usually we do not know that which direction we are going to get the maximum earthquake. That's the problem. So in very few situations in the world, that direction is precisely known. That in this direction we are going to get the major component and the other direction. So there we can make use of this information if it is there. But most of the cases in our country, there is no place where we have this precise information that in this direction I am going to get the maximum component of the earthquake. So in that case, we have to consider all the possible directions of the earthquake.
For structure resting on soft soil, the forces will be more. Whereas our concept is that the structure will attract more forces when it is rigid.
Yeah. So both effects are there.
Both, yeah.
If the structure is rigid, then also it will attract more force. If the structure is located on soil, same structure is located on soil and same structure is located on rock, then in the soil also, depending on the period of the structure. If the period is less than 0.4 second or 0.6 second on soft soil, then we see the flat range. Then as per our code, the force is not increasing. But if the structure is flexible and it is located on soft soil, then the forces are there.
What type of building base isolation can work? Low rise or high rise also?
Base isolation will work on hard or maximum medium type of soil and for low rise buildings. For high rise buildings where period is already long, actually base isolation works on the principle of elongating the period. So where the period is already long enough, there elongating the period may not work. And if we are talking about very soft soil, like the Mexico City I have shown, where the peak spectral acceleration is occurring at 2 seconds. And during Nepal earthquake, it was observed to be more than 5 seconds. So if that type of soil is existing, and there we provide base isolation, then base isolation will do harm in place of giving benefit. So while doing base isolated building, we should investigate the soil more thoroughly and try to see where we are expecting, at what period we are expecting the peak spectral acceleration. And we should not push our building into that peak.
Thank you. Next is, none of the codes give a clear value of cracking modifiers for spandrel. What value should be used for spandrel?
Okay. So I do not know whether our code, but there are some international code like LATPC which provide. So in that case, we can take, if anything is missing in our code, we can take help from other codes. But we have to be very careful. Few things can be borrowed, few things cannot be borrowed. So we cannot just mix them together.
Yeah, correct. Next is, in new code, map will be based on microzonation? Is it?
No, not microzonation. It is still macrozonation. but using probabilistic seismic hazard. Microjonation is one step ahead of it.
Yeah, correct.
So there, the variation of the soil, this does not consider variation of the soil at local scale.
Right.
So at the city scale, microjonation considers the variation of the soil within city
Yeah.
scale. So if microjonation or seismic hazard based on microjonation is available for a city, that will be better than what is given in the code.
Are there any plans for at least for major cities like Delhi?
It's already going on. For some of the cities, it is completed, but I do not know what happened to the report. Delhi, it has been completed long back. Jabalpur was done even before. Bombay, it was being done. In vicinity, I mean, in this Ganga, Yamuna, Doab, also in our Meerut and these cities, it was being done for. But I do not know what happened, whether that has been completed, what happened to the report. Kolkata report I have seen, that's already available on that.
But if some data is available, will code allow it? No, it's as of now.
Depends, because until unless those are accepted by BIS.
Yeah, correct.
So at least in those situations where microjonation is giving higher value, there at least we can. It may not, or the new code has come out with site-specific hazard assessment criteria, and how to accept that site-specific seismic hazard. Some committee formation, some administrative things are also given there. So maybe we can follow those. If we are not doing site-specific seismic hazard assessment and microjonation report is available, we can treat that as the site-specific.
There are no more questions from participants. I have one question. With these new developments, whether these large podium buildings with towers, which are the common in Mumbai, especially, where this it will go to almost time history analysis, because they are always in that range. But there are some simplistic methods people were doing that tower is analyzed separately and superimpose the reactions on the podium structure. So, which is a logical method that way. But whether it is whether it will continue or how
I think that's the only practical method.
Yeah, that is the only practical method. But
if you want to do analysis of whole basement, podium, and all the towers, it will be almost impossible.
It is almost impossible. So with this new,
that will be very difficult. So that is the plausible method, and I think that is accurate enough. Only, or rather conservative. Only thing is that when we are considering basement, we should consider the inertia force on basement also.
Yeah.
And that will be corresponding to 2.5, because period of the basement will be on higher side.
Yeah.
If we are doing that, it is conservative.
They are independently analyzed, so that it
is conservative.
That is
only if you want to optimize it. Suppose you want to optimize the design of basement, then you can go for time history or modal analysis of the structure as a whole.
Correct.
But that is very difficult to handle.
Yeah. Because if you can separate them, then it will fit in response spectrum anyway.
Yeah, and whatever reactions you are getting from fixed base, first of all, the base of the tower is to be fixed at the top of the basement, not at the foundation level. And then whatever reactions we are getting there, opposite of that needs to be applied to the whole basement model.
Yeah, that is a practical solution that can
continue. Is a practical solution.
That can continue, rather. Yeah. Okay. Fine. That's all. I think there are no more questions.
Okay, so I think we can close this session. And when we are meeting?
3 o'clock.
Yes. So
3 o'clock.
Yeah, over to you, Priya, madam.
Thank you. Thank you. So a big thank you to all the audience for being so proactive with the questions, because every time somebody asks a question, it is the rest of the audience that is being benefited, and everybody who will be watching the video recording of this presentation. So a special thanks also to our speakers, Dr. Lakshmi Parameswaran and Dr. Yogendra Singh, because you were absolutely on time, and that is such a great thing for the organizers, and it brings that nice feeling that we are enjoying and plus sticking to time. So wonderful going so far. Let me inform you that we shall be meeting at sharp 3 o'clock We'll be having a lunch break from 1:30 to 3. It is 1:30 sharp on the Epicons EFC clock. And we'll be meeting at 3 o'clock. A quick reminder with everybody's permission as to what exactly we will be listening and watching in the second half. If I may take a minute. After the lunch break at sharp 3 o'clock, we have two presentations. The first one by Lakshmi Parameswaran and the second by Dr. Yogendra Singh regarding two crucial topics. And the first topic will be, before I tell you the topic, let me give my two bit on these fascinating things. Times change, don't they? 40 years back, I remember we would go to our grandparents' house and we would stay in their bungalow and we would sleep on the terrace at night. And that simple G+1 bungalow had enough breeze and wind, which was so strong that we would sleep and it would make the sheets literally fly. And today, in 2025, we are talking about wind loads on high-rise buildings. Similarly, as far as earthquakes is concerned, I hear that we have a lot of legends of earthquakes from India, that how the world is balanced on elephants, which are standing on a turtle, and the turtle is standing on a snake, and every time all this shakes, the earth shakes. So all these legends and stories apart, these are the conferences and webinars where we stick to technology and all these things. So friends, I'll be closing here, and just to give you a summary of what the topics will be. The first topic will be Dr. Lakshmi presenting on design of buildings for wind effects, low rise, medium and tall buildings, how wind affects on buildings to be considered from design perspective, dynamic effect of winds on buildings, along wind, across wind response, aerodynamic interference, how to estimate wind effects, codal provisions, wind tunnel testing, and CFD. Dr. Yogendra Singh will be presenting on the topic analysis of design of buildings for earthquake forces and changes in the revised code on capacity design and concept of overstrength design. So fascinating things coming up in the second half. Have a relaxed and peaceful and great lunch on a beautiful Saturday afternoon. See you all at sharp 3 p.m. Logging off from me, Priya Gokhale. Have a great lunch. See you at 3.